I will announce the location and the date of the next GA at the end of this one. I mean, the assembly, the General Assembly, is a moment to take stock of what we achieved together. Not just to hear report or progress review. We do plenty of those. Oh, we have it. Okay, great. I can recover to my normal speed of speaking. No, I was saying it's not just about reporting. I know we ask a lot of reporting to you throughout the year, so while we are here at the General Assembly, let's not look at the reporting, but try to pick the whole picture so that we can see where we are going. And in a sense, this is what I want to offer to you this afternoon. A short view of where we are, how far we have come, and where we are heading. So 10 years ago, I joined ECNWF to work on C3S. So I decided on the program even before the organization, because I really thought it was an important exercise. And at that time, the program was already a remarkable achievement. It was a continental scale climate data infrastructure, openly accessible, scientifically credible, and operationally reliable. That foundation was, and still remain, extraordinary. That world, though, looks very different from the one we live in today. Many, many things have changed over these 10 years, in the world outside this building, as well as in the service. The service at that point in time, 10 years ago, was, despite all our best efforts, still speaking mostly to those who already knew how to listen. Specialists, a researcher, people who understood what our analysis was and why it was so important. What has changed since is not the quality of what we produce. I think that has been always very high. What has changed is the reach and the relevance of what we produce. The scale of uptake has grown in ways that honestly have exceeded our most rosy expectation. And in a good timing for the General Assembly, we just passed the 300,000 mark of registered user on the CDS. I think this is a sign of the relevance. We have user in all continents, and the user base keep growing. But our data set underpinned decision in sector we didn't necessarily originally design for. Finance, infrastructure, agriculture, public health, legal framework, even climate litigation is increasingly drawing on C3S data as an authoritative reference. Also, thanks to the National Collaboration Program, national adaptation plans across Europe are built on our products. Climate stripes on the walls of public buildings, temperature anomaly chart in parliamentary briefing, risk assessment on the desk of bankers. Much of that evidence traced back directly or indirectly to this community. Well, really to you, to the people in this room. We have built that evidence. But the change I'm most proud of is not in numbers, is the nature of the relationship between C3S and the world it serves. We have moved deliberately, and I think irreversibly, from being a data provider to being an authoritative voice on climate. We are no longer simply producing the evidence, we are helping to shape how climate evidence is understood, communicated, and used. That is a profound shift, and it carries real responsibility. It means, on the one hand, our scientific standard must be beyond questions, but it also means our communication must be clear and honest, even when we talk about the things we don't know. And it means we must genuinely be useful to the people who need to act on what we tell them, not just technically correct. This is the service C3S has become, and it's the service that everyone in this room has built. So just, I don't want to take too much of your time. Also, now that we have Siraj, I can speed up. But I want just to take a few minutes to highlight what looks like in practice across the pillars of the program, not to replace the detailed discussion you will hear over the next 3 days, but to give you a sense of the breadth of what we have achieved. On observations, the expansion of in situ data holding on the one hand, and satellite reprocessing on the other, has provided the data which made possible a transition in the quality of some of our most popular data set. I'm thinking in particular reanalysis. The work on essential climate variable represents a quiet but fundamental strengthening of our scientific foundation. Thanks to our closer interaction with ESA and EUMETSAT, We are now measuring more of what matters to the user more consistently and making it available in ways that serve both the research community and the operation. Dealing with observations, especially old observations, is at times an unglamorous work, but it's the bedrock on which everything else rests. On reanalysis, I will say very little on reanalysis because Hans Herschbach will actually talk in a few minutes and will do this subject far more justly than I can. But ERA 6 is now in production, and I think this is really a big achievement for the program. This is probably one of the most complete and accurate picture of the past climate that has ever been built. It is in many respects the flagship of C3S, and it represents a step change in what we could say about how climate has evolved. I really look forward to the presentation of Hans. Well, in a sense, I've seen it already, but I look forward to the presentation nonetheless. On projections, the Copernicus Climate Atlas could provide a new way for the program to interact with the IPCC, where this initiative originally stemmed from. Making the climate information available and accessible is not the end of the journey, and I'm sure Siraj and others will highlight this point. Often, many, many more steps are required to support local adaptation, but its first step, which is fundamental for starting the journey, is the data. On application, the work with the European Investment Bank stands out as one of the cleanest demonstrations of what C3S data can do when it's embedded directly into decision-making processes. We are talking about climate risk assessments underpinning investment portfolio of hundreds of billions of euros. This is not a research output. That is operational climate intelligence at a scale, and it's exactly the direction we need to go. On monitoring, the European State of the Climate Report as becoming something I did not dare hope for when we launched it. A genuine annual reference co-produced with the World Meteorological Organization, authored by hundreds of scientists across the continent, cited by European institutions and read by people who make policy. The 2025 edition that we published just a handful of weeks ago really describe, well, it was produced against the backdrop of what is already a remarkable year climatologically, without getting into El Nino territory yet. And it has an impact that you could see yourself. As many of you will know, we are starting to see the end of what has already been one of the most intense spring heat waves in this history of this continent. The European State of the Climate Report is designed to contextualize this kind of event and help explain. That is what C3S is doing and what it's for. And finally, the development of the reference climate scenarios for Europe in close collaboration with DG Clima. This has not yet happened. This is just in the plan. But it represents something that new and is very important for the program. A structured policy-facing interface between the best available climate science and the European institution that needs to act on it. This is the future of the program and what we want to work on with member states and with the people in this room. I will say very little about Copernicus 3. We are, as you know, starting now to look into that. And because of that, we have a session on Friday looking at the evolution of the service. But I will say this, the ambition for the next phase of the program is not simply to do more of the same at a larger scale. It is to deepen and formalize the interface between climate data, climate action at every level, from European policy to local adaptation whenever possible. The program will evolve to cope with evolving conditions around us. And I'm not just talking about socioeconomic, financial, or international condition. I also thinking in terms of technological condition, and in particular, artificial intelligence and machine learning. But the focus of mission will sharpen. It will provide authoritative, actionable European climate intelligence in service of a continent that is adapting to a climate it has never seen before. The people who will build the next phase of C3S are, for the most part, in this room. And I think this is actually something that I found genuinely encouraging. We have a very rich program ahead of us, 3 days of intense discussion. The themes of this year GA is user-centric, interactive, outcome-driven, and it's not just a strapline. It's a deliberate statement about what we want this gathering to produce. 3 thematic blocks will take us from scientific foundation of the service through the methods and tools that make our data genuinely useful, to the hard question about how climate information connect to decision and impact. In a sense, the program of a GA is only working if you interact with it. So don't hesitate to step in the many panel discussions that we have. Raise your hand and ask your question, even if probably mostly if your question is a difficult one. We want to have this question in the open in the moment that we are shaping the plans for the next phase. Before we start, I want just to say a big and warm thank you to Niels and Nicholas, who have put together a program I'm genuinely proud of, so well done. It's ambitious, it's varied, it's different from programs we had before, but it's been put together trying really to look at the needs of this community and the element we want to debate and at some point decide upon. Thank you both. Before getting into the nitty-gritty of the program and the substance, the observation, the output, the models, we thought it was good to look outside the program for a couple of keynotes, which will help framing some of the conversation we will have for the rest of the day today and in the next few days. So our first speaker is Peter Koiner. He joined us from WWF Hungary and brings a perspective I find particularly valuable at the start of an assembly, like our assembly. What do climate services look like when seen from the inside of a country already living with climate change? And what does it mean when you see it through the eyes of a civil society rather than government or science? So I don't want to say much more. Peter, the floor is yours.
Thank you. Good afternoon. And first of all, thank you for the organizers for inviting me and giving the opportunity to talk a little bit about the role of climate services in responding climate change issues in Hungary. So first of all, let's take a brief look at the European scene. From the European State of Climate report, we know that since the 1980s, Europe has been warming twice as fast as the global average. And within Europe, the CE region, which includes Hungary as well, is one of the most affected regions. We face increasing mean temperatures, more heat waves, more droughts, and more intense droughts, and heavy precipitation events. For Hungary, the first biennial transparency report gives a comprehensive overview of past trends of mitigation and the issues of adaptation. So let's dive a little bit into the Hungarian past climate tendencies. The Hungarian Met Service has over 200 years of climate and meteorological data for Hungary, and that shows that based on the homogenized observation data set of the Met Service, Hungary is facing higher temperature change than in Europe. Actually, compared to the temperature in the beginning of the 20th century, we faced 1.5 degrees Celsius rise of mean temperature. Furthermore, we get less precipitation in spring and autumn, while we are experiencing more high precipitation events and longer dry periods, and altogether this causes long-lasting dry soil conditions. The future projections show that most of these trends and tendencies are going to be continued in the future. Based on Hungaromet's in-house regional climate model simulations and processed Eurocordex data, the summer mean temperature may rise by more than 2 degrees Celsius by the 2041-27 time horizon. By the end of the century, the model results say that the increase of summer precipitation has a high probability, but we know that precipitation projects have more uncertainty included. While less precipitation in spring and autumn, we will face more high intensity precipitation events. So, to put it briefly, the key challenges for Hungary in climate change is the dual problem of water scarcity and water abundance. We are facing increasing air temperature and changes in precipitation frequency and intensity. More heat brings more intense evapotranspiration and less usable water for plants and living ecosystems and agriculture. We are facing more and more intense drought periods. So in the long term, the aridification in Hungary seems to continue. That is visible through the decrease of the groundwater levels and the lack of surface water quantities and the decreasing available water for ecosystems. That will mean a very high impact for agriculture, for industry, for drinking water supply, forestry, and of course the ecosystems. On the other hand, the model projections show that we might face more intense precipitation events, which may cause flash floods on small streams, mostly in mountains, and rapid flooding on major rivers. A very weird example of that was the 2024 year, the autumn, when the Boris cyclone caused a huge flooding in Central Europe. Hungary experienced not so high flood in the Danube, along the Danube, but a very critical one. While protecting the country against flood on the Danube, the Tisza region, the eastern part of the country, was experiencing a very serious drought. So all these say that we have to strengthen adaptation and resilience within the country, and we need and we must base on scenario and data-driven planning and decision-making processes. Some facts about what is going on now with the water problems. Today we are experiencing a serious drought period. You can see with the red ellipse circled our country, our smaller region, and you can see that these days drought is already in the warning and alert status. But an even worse thing is that the lack of precipitation and the lack of available water for the ecosystem is decreasing. This figure or this map shows that since 2007 the soil water index was decreasing in most of Hungary, as you can see it on the map. And an even worse thing that research shows that this process has been going on for decades now. And not only in Hungary, but in whole Europe or most of Europe, the soil moisture is declining since the beginning of the 1980s. This research shows that the annual average of soil moisture available to plants showed a downward trend across nearly the entire continent. Mostly the summer months became drier, and the region which was most hit by these tendencies is the Eastern European part of the continent. Firstly, Ukraine, Moldova, and Romania, but Hungary is also facing a drying tendency. And that is a serious impact for agriculture. Grain yields are becoming increasingly sensitive to fluctuations in soil moisture. So this research, which was made by Zsolt Pinke and his contributors, this research says that without large-scale restoration of wetlands, reconnecting floodplains, and holding back inland water, Hungary may face in the long term, large-scale land abandonment. So, as we are facing serious problems, we need to base our planning and decision making on climate services, climate policy monitoring, and its importance is growing in the European and in the global scene. So the EU adaptation strategy, the European climate resilience framework are all saying that it's important to improve the climate services and based on geoinformation-based decision support making and monitoring. The World Meteorological Organization also recommends to establish national climate change, climate service frameworks, and so the UNSCC Belém working program. According to that, the development of such systems is expected by 2030. In Hungary, climate services are quite well developed, operated by the Hungaromet, which is based on long-term meteorological and climate data. This very day, Hungaromet has started an open access portal, which is a one-stop shop for climate adaptation data and climate maps, from which all relevant database and maps can be accessed from. And we have a national adaptation geoinformation system with past data and projection data, and national climate change. The second national climate change strategy laid down the foundation of the Hungarian MRE system. And the National Adaptation Geoinformation System and the National Climate Change Strategies calculations were based partly on Copernicus data and Eurocordex projections. So, as we are facing serious problems and unavoidable changes, we need scenario and evidence-based planning using the Copernicus climate change services and other services. We need well-based strategies and legal framework to adapt to climate change and build a climate resilient country. And of course, we need closely monitor and evaluate the climate trends, emission trends, and of course the policy goals and policy implementation processes. Of course, companies have to make their own duties as well. Based on ESRS, companies have to make sustainability reports under the CSRD. So, as Hungary's climate policy has been mostly mitigation focused in the recent years, I think that the adaptation, climate adaptation and building a resilient society has a very high importance, and these decision-making and planning processes have to be built on the data-based systems. Our Climate Protection Act is under revision now. The country needs a stronger and more concrete Climate Protection Act. The National Climate Change Strategy is also under review, and its action plans will come after the strategy is renewed. So the work is there is a lot of work to do, and climate services will be extremely needed to do that work and make good projections and good policy decision making. Thank you for your attention.
Thank you so much for this brilliant presentation, providing a perspective from our host country for this GA. It's really important to understand what is happening at the local level. The other introduction today comes from Suraj Desai. Suraj and I actually interacted over the years, and I always find his word surprising and inspirational in many respects. Today, he will be speaking on behalf of the European Scientific Advisory Board on Climate Change, and will offer an independent European view on what strengthening resilience in Europe actually requires from us. Suraj, the floor is yours.
Thanks, Carla. I'll just open this up. Great. Can you hear me okay in the back? Brilliant. So yeah, good afternoon, everyone. Let me start by thanking Copernicus and the Hungarian Met Office for organizing this event, and your very kind words as well, Carlo. I'm delighted to have been asked to come and help frame some of the discussions we will have in the next 3 days by presenting the Advisory Board's recent recommendations on strengthening the EU climate adaptation policy framework, which we published in February this year. You can find it online. I've got a copy here. And then also discuss a little bit the role of climate services could play in adaptation. Does that work? It works. So before I do that, let me just introduce briefly the European Scientific Advisory Board on Climate Change. The Advisory Board was established under the European Climate Law to serve as a point of reference for the Union on scientific knowledge relating to climate change. It consists of 15 independent experts. You can see them all there. I'm pleased to say we have a Hungarian colleague in Vera represented in the board as well. So we cover a range of disciplines related to climate change, from the natural sciences to the social sciences to law as well. And we're supported by a secretariat that's hosted in the European Environment Agency. And our role really is to provide, as Carlos said, independent scientific advice grounded in the best available evidence to inform EU policymaking. And we had a first term that started in 2022, that finished in March. And this particular report that I'll tell you about was launched within the first term. These are the members for the second term. This is a 4-year term. So our adaptation advice comes in a context where there's clear climate change, and our colleague, our previous speaker, and Carlo have already alluded to this, that climate change is no longer a distant, abstract risk for Europe. We've got, you know, Europe is experiencing increasingly frequent and severe climate-related extreme events. And you can see quite a lot of examples here on this slide. Some of them relate to repeated floods and storms across Europe. You'll remember the Valencia floods of 2022, but even, you know, earlier this year we had quite a lot of flooding in Portugal, Ireland, Spain. Heat waves, droughts and wildfires have intensified across Europe, causing thousands of deaths and record wildfires, for example. And even just last week, again, more records being broken in Portugal, where I was, but also in the UK and France. So all this adds up to very large economic losses. So we're getting in the order of 45 billion euros average annual damages to infrastructure over the past 5 years. So that's roughly 5 times more than we had in the 1980s. And finally, I mean, as extreme weather events become more frequent, severe, and widespread, they increasingly compound one another, making climate impacts more significant and difficult to recover. And again, we've seen many examples of this in past heat waves, flooding, and other events as well. So, unfortunately, the climate is going to continue to warm, given past emissions and committed warming. So we are going to continue to have more intense and frequent widespread hazards, such as the ones you can see here on the left. And of course, this also interacts importantly with exposure, vulnerability, and also responses, which is the new way, for example, the Intergovernmental Panel on Climate Change is talking about climate risk. So these risks threaten people, ecosystems, and the economy. And we know that climate change is a major driver of biodiversity loss, poses growing risks to human health, threatens food production, and critical infrastructure. And we also know that these impacts are increasingly systemic. So climate impacts can cascade across highly interconnected European systems. You can think about food, you can think about supply chains, you know, etc. So we live in a very interconnected society, and climates, you know, not only, you know, extreme weather events in the EU, but also things that are happening outside the EU are also having an impact. So this then spreads throughout the economy and also natural systems. And particularly important as well is that these risks then eventually threaten and undermine the ability of the EU to deliver many of its strategic goals, such as competitiveness, cohesion, you know, food security, etc. So adaptation is really necessary across sectors to address the systemic risks that threaten the security of critical services like water, food, energy. It's needed to provide the stability you know, to invest in a competitive and innovative economy, and also to help protect the health of EU citizens and its ecosystems. So I want to speak a little bit about the EU role here, which is quite important. And again, a colleague talked a little bit about this already. The Commission is preparing an integrated resilience framework. And I mean, what our view is in the advisory board is that adaptation efforts need to accelerate, and the EU has a distinct role to play in, you know, coordinating efforts that are needed in this space. So there's been some progress in adaptation in the last few years, but there's still quite a lot of barriers, such as limited information on risks, you know, incentives, institutional constraints as well. So addressing these barriers requires public intervention, but local and regional authorities, for example, which often are best placed to drive adaptation. You can see the sort of scale here from local to national to EU level on the slide. Very often, you know, local and regional actors are very constrained in terms of resources, technical capacity, and access to risk information. And even national authorities as well can address some of the barriers, but they also face similar constraints as well in terms of, for example, managing, you know, transboundary nature and climate risks. We're sitting next to the Danube, so that's a great example of a transboundary risk that does need to be managed across different member states. So this is really where the EU plays a key role in providing coherence, scale, and long-term direction through a common approach to risk assessment and coordination, stable policy frameworks to enable long-term planning, shared tools and data and support action. So, I mean, I think C3S is a great example of this. And the mechanisms to ensure fairness, solidarity across regions with different vulnerabilities and capacities to adapt. So the EU has taken steps to integrate adaptation across policies and funding, but progress really needs to accelerate, and implementation is really not keeping pace with the escalating climate risks we're seeing across the continent. So let me move on to our recommendations for an EU adaptation policy framework that's effective, fair, and transformational. Is that going? Ah, there we go. So first off, effective adaptation really depends on understanding current and future climate risks and acting before these impacts materialize, but this doesn't always happen. We have lots and lots of examples of this. So the EU should, one of our recommendations is that the EU should mandate climate risk assessments across relevant EU policies and decision-making, and that this should be supported by common climate scenarios, and Carlo gave us a prelude that they're working on this already at C3S with the Commission. And this should be co-developed between the EU and national member states, for example, Copernicus, national Met offices that are present here as well. And the EU should establish a common methodological standard for risk assessment based on key parameters such as time horizon, sectors, update cycles, and so on. Secondly, we also recommend that we have a shared reference to ensure we have a minimum level of climate resilience across the EU, and also to further improve consistency in risk assessment and planning. So I want to stress that adaptation is about managing risk, and clearly rapid decarbonization in line with the Paris Agreement remains the best way to limit climate risks, but adaptation planning really needs to be based on actual climate conditions that Europe is going to face. So a precautionary approach really is required here in preparing for the physical risks associated with current policy trajectories. So we looked at the evidence, and so we recommended that the EU should adopt a common reference based on IPCC SSP 4.5, which effectively means preparing for a pathway of global warming of between 2.8 and 3.3 degrees Celsius by 2100. And we also stress that we should do this, but we should also stress test against more adverse scenarios, like, for example, RCP 7 as well. So we clearly need to use a range as we are preparing the entire continent for a changing climate. So third, we really need a clearer and legally grounded vision for what Europe, for adaptation in Europe. So that this really needs to be embedded in EU governance framework so that we can strengthen the policy direction, coherence, and ensure it's aligned with science. The current EU vision is too general to drive adequate action, and we really recommend setting a clear vision for a climate resilient Europe by 2050 and beyond. And really, this really needs to be supported by sectoral strategies, and in particular, looking at sectoral and measurable targets for adaptation so that can drive progress and ensure accountability. Number 4, climate resilience needs to be systematically integrated across EU policies and investments by applying resilience by design principle. So this should be underpinned by monitoring, evaluation, and learning. So this, for example, could be supported by the various Copernicus services and ESA, for example, who's trying to track, for example, adaptation as well. This also needs to ensure that policies lead to fair and just climate resilience that addresses unequal impacts, enables meaningful participation, and avoids regressive outcomes. And our final recommendation is around adaptation, investment, and finance. So given the increasing economic strain of climate impacts, climate risk management needs to be embedded really in national and EU economic and fiscal planning. So early and sustained investment is key to limiting harm caused by climate change and maximize the benefits. So to that end, the EU could strengthen the contribution to resilience on the next multi-annual financial framework by applying a resilience by design principle across funding. The EU should also seek to strengthen efforts to mobilize private finance, help address the insurance protection gap, and strengthen response mechanisms. So I am on my final slide, Carlo, so just to reassure you. So implementing these recommendations and accelerating adaptation efforts will be crucial. And that's where the work being done by everyone here in this room is so important. Climate services provide the analytical foundation for adaptation to understand climate trends and provide the detailed information needed for risk assessment and adaptation planning. But climate services aren't just about better data. It needs to provide the timely, usable, and user-centric knowledge needed to support decision-making at every level of society. And it's great to see the various themes that Carlo introduced earlier being very well matched here with many of the recommendations we've made in this report. So we also need to ensure that the right information is reaching the people making the difficult decisions on how to adapt. That's why we called on the Commission to strengthen EU monitoring, evaluation and learning systems to support adaptation, as well as ensuring any common climate scenarios are co-developed with organizations such as Copernicus and National Met Services to make the best use of knowledge and expertise here in the room. So for the next days, I can see these challenges will feature heavily across the talks and discussions, which I'm really looking forward to, and to explore how we can tighten the links between climate services and strengthening resilience to climate change. Thank you very much.
Thank you, Siraj. Thank you. Well, actually, Siraj, I was honestly just looking at my watch. I wasn't signaling you to go fast. You were spot on time. And thank you for making all these references. I think these two talks work really well together and link to many of the side events we had this morning. So we had a Hungarian event looking at what's happening in Hungary, understanding what are the needs of the country and what is already taking place. But we also had the National Collaboration Program, where some of the elements about transboundary action that you mentioned, Siraj, as well as training, actually have been addressed. Now, let's jump to the session itself. We start to get into the nitty-gritty of the program. And we decided, as I mentioned in my introduction, to start from the basis of everything we do, which are the observation. We'll have two talks on observation, one on satellite and one on in situ. And the first talk will be from our old and good friend, Jörg Schulz, friend of the program since the very beginning, and probably one of the persons who has done the most in reprocessing satellite data and making those available to reanalysis. The third talk will be on reanalysis itself. Jörg, before I give you the floor, I just want to make a couple of almost housekeeping points. The first one is that I will only take one question at the end of each of the next three talks, and I will take the question of the first person who put the hand up. So there is a bit of a competition. If you want to ask the question, be fast. The other question will be taken at the end. I will ask the speaker back on the stage, and we can take those. Second, given that we are all aging and maybe 5 talks in a row is a bit too much, I will ask you to upload each of the speaker with 7 claps, right? Right? That should be coordinated. It won't work, but it will probably crack a laugh. So that's the rule for the next three speakers. So before, without further ado, let me just introduce Jörg and his talk. Jörg, floor is yours.
Very good first try. So thanks, Carlo, and it's a pleasure to be here and to talk to you about some of the foundations. And I basically put my whole team on this, and it has grown over the years very much. And this is also thanks to the collaboration with C3S, but also with other Copernicus services. So just to give you a connection to what we just have heard and to illustrate how complex that is. So this is what the space agencies, and not only EUMETSAT, basically call the climate monitoring architecture from space. It was mentioned in the beginning. And this is, you go from satellite observations, and then we try to do some what we call climate data products, and they go into applications, and then there's this big block we just heard about on policy and decision making. And these are really distinct communities that speak very different languages. So it's a pretty complex process to turn data and missions of satellites into an information that is actually useful downstream. And I think the last 10 years, there has been made a lot of progress in that direction to make that a much better working and different activities of the Copernicus services, but also of the space agencies, including ESA and EUMETSAT, to make that a process much better. One thing that we have tried since a while, almost 10 years, is so do we get a better handle on our estimate uncertainty in our measurements from space, and how do we transform that into a level of confidence in the policy and decision making? So you all know from IPCC reports, they always talk about the confidence and statements they made, but this should be rooted actually on that we know something about the uncertainty, and that is also something that would concern the reanalyses, for which it's very difficult to constitute a real uncertainty as you can do for observations. So this is a topic many have worked on, but it's not a finished topic, and there might be a lot to do in the future. To make that successful, what we really need is we need needs of the policy and decision making, and this is turned into requirements, so for products, but also for space-based observations. And that is a very difficult process as well, because they speak different languages. So formulating needs that would be pointing to the right measurement that you do from space is not an easy task and involves many people. And you need to have a mix of research and operational measurement missions that not only serve climate, but also weather, environment, and many other things. And it's a good mix of skills that are required to do this. But to have good products, there's so process for design and development works from the right to the left. In the very past, it was just the opposite. It was always going left to right, and then you are confronted with products that you have difficulties to use. And I think we have improved a lot, but we can still do better. Research is basically needed across all these domains because nothing is perfect, as you know. So from our member states in EUMETSAT, so there are a couple of major requirements on the space mission data. So what they task us basically is we really need to assess satellite data needs from all these sectors and policy, services, and science to do this transfer into what is needed also in future space-based observations. Maybe we missed something completely that we should rather measure much better than before. There's early involvement in users in product planning and design and co-creation. And I think the best example is actually the provision of the data for the reanalysis, where we have learned a lot on what data to provide, in what form, and how this could be successful. And you'll see an example later. User needs for the EUMETSAT climate data. You know, we have also this network of satellite application facilities that produce also data records. Some also be found in the C3S data store and are very useful. But what is really needed is a long-term continuity of the space-based observations, and believe me, that is not a given. This is something which each program you need to work on that. You need quality control, gap-free, consistent records with long-term continuity. Reanalysis is one answer, but not the only. You need highest possible spatial temporal resolution. This is even more emphasized because it comes with the concentrations on understanding and predicting extremes and these kind of things. And we need to deliver this also low latency. I put here just less than 5 days, which is a bit arbitrary, but this is the expectation where this climate quality information needs to come, and we know that C3S is also doing that. Then there were other things. The last one is a technical thing that's also important, and data discoverability, accessibility, documentation, interoperability. So we have data stores, still many, and they're still not interoperable. If you go into the worldwide level with the United States, there would be an endless amount of work that you can spend on that. Okay, but why we engage in reanalysis? So why was that so attractive for EUMETSAT to do this? So of course by now we have learned that I think the number is changing all the time, and Hans would have a much better number. But the last one I recorded was about 200,000 users for Era 5. So that's great. That's a super amplifier for the use of our satellite observations. So that alone is super successful. And we see this in all these climate state reports, and then it turned out to be also a good training data set for AI/ML weather forecast model development, and then now there are other approaches that even bypass the reanalysis, but if that is successful, we will see. But even more important is it has also a lot to do with the process, how we work. So it really drives consistent improvements about the science components of the Earth system science components, so the quality of observations is very central to the assimilation and reanalysis. So we have learned a lot how to analyze that. There is the models, the data assimilation principles, AI/ML, computing, data access. It's a whole plethora of things that we have improved and sustained over the last decade. The reanalysis outputs, and this is still concerns that I hear sometimes in other frameworks, it has various degrees of quality. So some parameters are super good, and some others which are less reliable, because so if you think about Earth's radiation budget, that might be something you may not take from reanalysis straight away. But this is something where one could really express probably a little better. It's tied to the uncertainty analysis, but also about giving the quality information, because the users believe you everything because you're so credible, and they take everything and may do something that is not correct with the data. What we really did is, at least in the second phase of Copernicus, so this is a slide of historic satellite observations. It starts on the left somewhere in the 1960s and goes then to the later days in 2005, and you see data in blue that were assimilated, not in Era 5, so they come all for Era 6. And then there are some in dark which had been assimilated but could still be improved. And we have basically formed a trilateral cooperation. So there's the company Spacia, they are also here. We had a nice meeting in the morning. And with ECMWF to really work on all the data to get them into the reanalyses. And most of these data, as you can see, have never been used. So there's a real impact. And we now see, after about a little less than a decade of work, how successful that is. And that's really great to see. It needs a long breath, and as Carlos said, it's a nitty-gritty detail. No? So it's not like, oh, wow, that's very shiny. No, it's really a nitty-gritty detail, but it's very important to improve. And to just show you two examples, the one thing that EUMETSAT has worked is a lot on microwave and infrared sounding instrumentations, as they are really important to basically reduce the forecast error in the weather prediction. We know that, so they would have the same importance in the reanalyses. And there were, of course, data that have never been used, like the SSMT temperature sounder or the T2 humidity sounder. There's an infrared sounder, SSH. This was really discovered. Nobody knew that this actually exists. And we have worked these data up, and what you see here is basically the error reduction and the reforecast done by the reanalysis, and everything that's blue is a big success. And what you see here is very dark blue, so for the T+12, so southern hemisphere stratosphere, where this SSMT has two channels which are in addition to the classical MSU channels. So that's a great success. When I saw that picture first, I said, yeah, every minute was worth it to put into the SSMT data, and this I haven't done myself, but my people have done that, and that's really good. We have done a lot of other data, so that you see below, like radio occultation data, HERS, and more modern sounding data, just to make them consistent in the use for the reanalyses. And you see even on HERS, that is a sort of classical IR sounder that has been used since ages. We still could significantly improve that by just doing a consistent calibration of the time series. Another thing that's quite significant, there is it's also an infrared radiometer called the CIR. And so that was analyzed and rescued by Spacia, and we got the radiances from them, and okay, they are pretty noisy, so it's not easy to assimilate, but classically, a reanalysis like the weather forecast is also assimilating atmospheric motion vectors. And so can we do atmospheric motion vectors out of that? So it's less spatial resolution than you are used to from AVHR or more modern infrared images. And then we just took an algorithm that we had for AVHR and minted it into the circumstances of the CIR radiometer. And then we were able to derive atmospheric motion vectors. So this is over the North Pole here, and you see all AMVs of one single day. So it's not a big turnout compared to modern instruments, but still much more compared to no information. And you see the geopotential height on noon on that day, and you see that these wind vectors are pretty well aligning, not everywhere, with the pressure field. So there is substantial information in there that could be used. And I just learned in the morning that there will now be a trial still for ERA 6 to probably assimilate those data. So they exist for about 8 months in 1970, and then there is a few years later a much longer record of that. That is even in a different orbit. And you see the comparison to ERA 5, where you see most winds are at about mid-level 500 hectopascal, and it has biases and RMS errors which are very comparable to modern instruments AMVs. In 1970, I think that's quite significant, and there were some other data which are even in the late 1960s. So this is a real achievement of the program. We work outside of that also on something that's called the geostationary ring. So this is not within Copernicus, but Copernicus will hopefully benefit very much from that. That's a collaboration that we have with NOAA and also the Japanese Meteorological Administration to bring together basically all the geostationary measurements of the past. And there's a lot of rescue done on the US side so that you can end up to have all these measurements that you see on the left with about 30-minute temporal resolution back to the 1970s. And this is something that doesn't exist yet, but we are working on that. And there's this white slab that you can see in the left plot. That is where the Indian Ocean measurements, and we still work on getting data from India, and they look also not too bad to be included in this. And there's a paper that we published, I think, earlier this, I think it was coming out in February in BAMS, where you can read a foundation of this. So this is how it looks like. There's already a test data set. So this is harmonized Severi Himawari in 2023. So that's an 11 micron. And where you see this seamless radiance that comes on a HealPix grid, 5 kilometers square, 30-minute resolution. And this you will get back to the 1978 globally for all geos. And this is the Cyclone Freddy, so that's just the one that killed a lot of people. So this is pretty cool. And this is really QC. So everything we learned from all the other sensors we have applied here, from individual pixel radiometric quality, everything is in there. And you can download that test data set or go on the European Weather Cloud. And then next year you will get this starting in mid-1970s, a full record. This is good for assimilation. You can apply retrievals, but you can also use this in AI/ML. So we'll also go in AI-DOP approaches for weather forecast. And we have been already asked to do this in lower latency and possibly even in NRT, because that you would need for the weather forecast. What the plan is that this is only going to about 50 degrees north and south, so we will integrate that with data from polar orbiting satellites and make this a global product, and then we may add other things like lightning imager data and other information into this. And you see the cyclone, so this is also depicted by an AI algorithm that can produce storm information directly. Is there more data rescue? Yes. So we have still a continued collaboration with NOAA on data you saw on this time chart I showed earlier on ATS. So this is just a visible channel. And this is what you see in the middle is the first colored picture ever from space on 10th November 1967 from a satellite. And NOAA is working on that. So ATS-1 starts in 1966. And this has about 63,000 images which are digitized, so basically from card box into digital values. So we will try to integrate that, rescue that, and then it could be for next 3 analysis assimilation. You can also use that data to learn something about the climate system, actually. And so we build also climatology only based on Meteosat of convective systems over Africa and Atlantic. And you can get that also. And with that, if we just, so this is deep convective system occurrence. And on the right, you see the trends in the occurrence of these systems over Africa. And you can really derive from that, so where these trends, so everything in black dots is significant. And you see the yellow, which is a decreasing occurrence of these systems, and the red low is an increase of the existence of these objects. So that gives you an indication how this is changing, and you can use that to put constraints on convection model at process level. That has already been done with ICANN by Max Planck and Hamburg and others. And it also helps answer questions, organization of deep convective systems, and how this is represented in cloud-resolving models. So where the modeling in physical sense goes to the so-called kilometer scale, this is a very useful data set to be used for that. And there's also a nice publication that describes this finding. Last slide. So where to go from here? So I think what is important also for C3S, but also for other Copernicus services, so we need to make climate-strong emission planning. So the continuity isn't automatic. You can easily lose a channel or something like that because other parties think that it's more successful to do it this way than that way. And then they do an abrupt change, and this would not be in the favor if you are interested in a long record. Downstream application understanding, yes, we need to continue understanding that better in the future. I think this will never stop. Data and products, so we will introduce the co-design process into the planning. We will continue data rescue basically until nothing is left to do. We might get to an end at some point, no, because then there are only the Russian archives left, and I don't know what's in there, and we have no access to it. But we would extend time series of similar data and combine data for easier exploitation in AI, ML. So this is for example, the extension of the georing, but there are also attractive combinations, for example, of current Copernicus measurements like SLSTR backwards with MODIS, and put this together in a consistent fundamental record, and you can base lots of retrievals like on aerosol, optical depth, and things like that on that. That's also part of the future program. And the uncertainty quality characterization of satellite data and derived products, including Fourier analysis, is something that one should also follow up. And the rest is technical, and the major message is collaborate and continue that. Thank you very much.
I think there is a good margin of improvement on the 7 clubs, but yeah. Let's see on the question, how are we doing? Stefano.
Yes, radar data, of course. No, so that's not space. You mean space-based radar or surface-based radar?
Surface. I was thinking about surface.
Okay. We also think about space-based radar.
So of course. But those I gave almost for granted.
Program, yes, on microwave imaging data, which I haven't shown, but that is something with the UPSSG. We have now a microwave imager, so we're going to care for the whole history of microwave imaging as well. Space-based radar, so we work on that in the context of machine learning. So that is existing, and I think we have with EUMETNet data in the European Weather Cloud. Now, so EUMETSAT is hosting that, but it's together with ECMWF, and this is already exploited, in particular also for nowcasting applications. So it's not so much on climate, because the heterogeneity of that data, I think that uses about 20 people to get that fixed. So that's a work what people could do, but that's probably not necessarily a program for the satellite agency. Maybe.
Thank you. I feel that actually the debate at the end may be very short because we are running a bit late, and I know you would need the coffee. Well, anyway, thank you very much, Jörg. Before you go, knowing that this is the last GA of C3S that you attend in your EUMETSAT capacity, I wanted to donate you wooden duck, the symbol of ECNWF. I know being at EUMETSAT having a ECNWF branded one can be controversial, but you are such a good friend of the program.
Thank you, Carl.
Thank you. It's been a great collaboration. Thank you. Okay, next speaker is Barbara Cimani. She will be taking us from the sky down to Earth and looking at very much the in situ component, seeing from a EUMETNet perspective. Barbara, floor is yours. Thank you.
Okay, I assume that, or I can assume in any case, that all of you know what C3S is, but I'm not sure if all of you know what EUMETNet is. So let's start the explanation of this abbreviation on this slide. So EUMETNet is a network of 33 European met services, so national meteorological and hydrological services, that are working together to increase the potential of what they are doing. So let's move forward. And having said this, it's clear to you that there have to be some connections to C3S, because net services are working or collecting data. They are doing caring for climate aspects, and so HumanNet is having the same topics. So when we talk about the in situ data, this in situ data is the backbone of all the climate information and work that is done or available. If there wouldn't have been started to have measurements quite some 100 years ago now, we would only have some descriptive information on climate extremes from some personal diaries or some business business journals. But so we have really clear information and what is going on in the current climate, in the past climate, and also regarding climate change. And they are used in nearly all the climate products, either directly or for evaluation or for creating the data set. Let's start with the observations themselves. There are already some topics that I have a connection between HumanNet and C3S. All the Met services are responsible for the national measuring network, for the in situ and also for some remote data. So what is in situ data? In situ data are measurements where the instrument is placed at the location of the measurement itself. That's, for example, something like the traditional stations we have seen on the last slides, or radiosondes. So while the Met services are taking care of the national network, HumanNet is taking care of the most expensive measurements that are, for example, done on the marine by ships or by boats or from airplanes. And I squeeze in here some remote sensing data as well that is collected by the Met services or by HumanNet or analyzed, like the data from the global navigation system, where you can retrieve some humidity data. When you look now on the web page of C3S, you will notice that a lot of those data sets can be found in the in situ section. The data that is collected by the Met services or HumanNet and is distributed mainly for the forecasting purposes is turned to some climate data set and included into the quality assurance system they have installed in C3S. This is just some part of the data available. The slides are a little bit limited what you can show. To have this data, it's not only measuring the current data, but it's also going on data rescue. So data rescue means you have a lot of data still in paper archives all over the world, and you have to scan and digitize this data so that it can be used with computers and analyzed. This is done by Met services, and in 2013, HumanNet started some activities to support these activities from the Met services in discussing best practice and also exchanging data that is available. As you can well imagine, during the changes in the political situation all over Europe, some stations might be in another archive than they would be nowadays. And the data management workshop, which is still taking place every second year, was created to support the exchange of those activities. C3S started a very big data rescue activity in 2017, focusing on especially on the data sparse areas, but covering the whole world, and having a lot of material for, to support a data rescue in this regard. Recommendations for data providers as well as supporting material. When we have collected a lot of in situ data, we can do gridded data sets. This is done by the Met services for the national or regional areas. Within UMetNet, the European gridded dataset EOPS was developed starting in 2004. It covers the whole area of Europe, as you can see in the picture beside here. And it covered the different temperature parameters as well as precipitation and sea level pressure. This dataset moved to C3S in 2017, is now provided there together with some other in situ gridded datasets, and was enlarged with further parameters in the meantime, like radiation, humidity, and wind speed. To improve those datasets even further, open data is an essential point. Met services provided some data all the time as soon as web pages were formed. It was mainly processed data on climate normals or extremes. But with the open data policy, all of them started building some open data portals to provide the data. Nevertheless, within UMetNet, they decided that they would like to have one central point to distribute all their meteorological and climatological data together. And this was created in a project Rodeo on an EU call, and the product was MeteoGate. For C3S, the provision of data for everyone and all the purpose was the main aim in the beginning already. So, I would like to talk a little bit more about this MeteoGate and the climate aggregator part of it now. In contrast to other data sets in UMetNet, there has never been any collection of the climate data before from the different Met services. So it was really starting from the scratch here in the climate part. Moreover, there are some difficulties as all the databases in the Met services, of course, are structured a little bit different. Everyone was doing it according to their needs and on their surrounding. So you might have tables structured differently, you might have named them differently, and things like that. So what wasn't built now? When a request from a user on climate data comes, it is passed to the climate aggregator, and this climate aggregator API is sending a request to all the Met services included. All the Met services send the answer of the request to the climate aggregator. The climate aggregator is putting it into the same format and sending it back to the user as one data set. Beside the national APIs, you have also that API to the ECA and D dataset, and we will come to this point later. What's the benefit of the climate aggregator? You can access data of all regions for the whole of Europe in one request. You can request it with an API, so it can be done automatically. You can get a lot of data, so you can use it for AI applications. If you send a question to the data to the MeteoGate, and it is not something technical that they could answer, they will surely bring you into contact with the data providers, so the National Met Services. You have a direct link to the National Met Service database, so you don't have any outsourced data, but the latest version of the quality control data there. You will receive some standard formats, and for C3S, the main point is that it's a very fast access to all the data available. I'm working with in situ data all my professional life now, and I know that it's really worth working with this data. Nevertheless, there are some points you should take into account. the quality control data is controlled for the time when it was measured. So it might have been another instrument and at slightly a different location in 1900 than today. They try to have it undisturbed. They might have to do some relocation of the station. And the most important one, there are quality flags. Take them into account. They give you an important information. Everyone, also me, tends to ignore them, but that shouldn't be the case. Where do you get the data? You can get it in Meteorgate. It was done as a, it's not finished now, it's still under development. At the moment, there are 7 countries included. The others will follow in the next time. For the others, at the moment, you have the ECND data, which you would make a separate request for. Be aware that this data was selected once for the EOPS data and might not be the last version of the data that is available at the Met services. Regarding the next plans for the climate aggregator, it's onboarding of the additional Met services, which would be about 10 this year. There will be a connection to the WIS2 Global Discovery Catalog. The ECND database will be included into all the queries, so you don't have to do a separate one. The climate aggregator code will be open source, and there will be an adaptation to the European Weather Cloud. When we look for further possibilities to work together with C3S on in situ data, the first data set that comes in mind would be some phenological data, which is already available. It's not as measuring or as, it's not in situ from the meteorological side as the other data we are talking of now, but it's a very important data set with a lot of publications every year giving you information on the time of blooming or ripeness of fruits. Another option would be some might have noticed that I just slipped one small sentence and one on the slides regarding securing some already available climate data sets that will be important for the future to ensure that they will stay available. With this, I would like to close this talk, thanking everyone involved in the rodeo, especially also KNMI. We've had a lot of in-kind contribution to this, and EUMETNet is at the moment in charge to ensure the sustainability of the climate aggregator, and in this we would also like to thank ECMWF and C3S for the interest in using this climate aggregator and in supporting its sustainability. Thank you.
Getting better. Thank you, Barbara. Thank you very much for your talk. If you want to take a seat, we'll move rapidly to the last talk of this session, and we'll have a very mini panel discussion at the end so that we can go for the coffee. The third talk is from Hans Herschbach and will be about, well, I think the title may take away part of it, reanalysis, but a sneaky preview of Year 6. Hans, the floor is yours.
Good afternoon. Thank you for inviting me. So I'm in charge of the reanalysis team at ECMWF, and the first 7 or so names of my team members. We've been working very hard on Era 5, also Era 6 now, but there's many other people also involved. So many in ECMWF, but also outside ECMWF. So those are scientists, but also people that look after the data format and these kind of things. So, and also make sure that we are able to sorry, up? Yeah, okay, good. Make sure that we can produce all these petabytes and that they all go to disks and tapes and things like that. And also people that have been evaluating some Era 6 prototypes that we have made available in the last 1 or 2 years. Okay, So first I will say something about ERA 5, then I talk about ERA 6, I show some case studies, talk a bit about observations, has been said a lot about it already, and then summary outlook. Fine. So this slide I've showed several times already. The next slide I've showed already as well, but the rest is all new. So ERA 5. So ERA 5, yeah, it's a very successful data set. It provides climate data from 1940 onwards. And if you look at the quality, so higher is better than the plot of other reanalysis is better, and it's also the longest period. It has many users, 200,000. It should be more, I think. Yeah, we have also many scientific citations. So last Monday we reached 30,000 citations for the ERA 5 paper. So that's going really, really fast. And also the estimated economic value is quite high. We did a study, and a number came out of about 1 billion euros of economic value a year of using reanalysis and ERA 5. So there's many applications, is active timely climate monitoring, people are interested in particular cases, but of course, yeah, machine learning in the last few years, ERA 5 has been really extensively used for machine learning, and we are able to beat physics-based forecast systems with that. And I think most of this economic value comes from machine learning. Okay, so going to ERA 6, so we benefit from an additional 8 years of R&D at ECNWF, and also make use of that computers got faster. It will be 14 kilometers rather than 31 kilometers it is 14 kilometers compared to 31 for ERA 5. We have an EDA as well to grasp the uncertainty estimate, that's at 28 kilometers. We now have an ocean model as well, so but the ocean data simulation we don't do. So we get the initial state, we get it from the ORA 6 reanalysis. I should have mentioned that here. So we get it as an initial state, but then during the assimilation and the minimization and also the forecast, we are really two-way coupled. We solve a number of known issues about of ERA 5, like taking better care of stratospheric biases. We have a time-varying urban tile as well, and we have a better initialization of soil moisture because of ERA 5. We had jumps in soil moisture between production streams. And actually that was developed, we did a run from 1939, which we will use all the way up to a few years ago, which we use an initial state to initialize ERA 6 soil moisture from. And that was done within the C3S project, it's a European funded project. We adjust the best observations, as already Jörg told you. So we do it together with EUMETSAT and Spatia, but we also have in situ. We do a lot of in situ reprocessing and data rescues. That's together with the Maynard University and their partners in the contract. Then reanalysis is also a lot about products. I mean, we produce a lot. That is all based on user requirements. Users want this. We have a very rich spectrum of users that have all their own kind of requirements. So what is new now in ERA 6 is we have this 3D and also 2D ocean parameters. We have height levels for the renewable event industry. They really would like to have height levels. So we have them. They are based on the same height levels that are used in the CARA and the CARA 2 and the SERA reanalysis, which will be the next talk. They're 11, from 11 to 500 meters. We also have snow levels. Everything is hourly again, but we have a number of new parameters. Like 2 meter relative humidity, a rule that is for reciprocal Obikov length. So that gives a measure of the stability of the air, and we also have clear air turbulence. Now about statistics, so it's all hourly data, it's a lot of data. We have monthly data in ERA 5, and one of the first tweets when Twitter was still around, it was like, okay, it's all great, ERA 5, but we also want, what about daily? So now we also do daily aggregations. We pre-calculate these daily statistics. And everything is a grip 2. So that will be quite a revolution because some certain things are different. And so there's a lot of data. It's about between 30 and 40 petabytes. So it's about 4 times more than Era 5. So how I'm going to download all that data? Well, you don't need to. We have efficient ways of that people can plug out only the bits of pieces that they need. So for instance, this is Polytope. Our fields, they're fields like this, like lasagna sheets. And for each day you have one global field, but some people they want like this spaghetti, and then you have to get all these lasagna sheets in order to get this spaghetti line. And now with the Polytope you can do that in one go. You don't have to retrieve all those fields, so that's much more efficient. Good. So Era 6 is in production. So we started now, and so where are we now? So this is a plan, so I'm not going to say that it's all going to happen exactly as I'm telling you now, and these quarters, they may shift a little bit. So we run it in streams of 10 years. So we started 2 streams now, a stream that is actually started from 2007 and for 2017, so we have a 1-year spin-up year as well. So they're running now. You can see there, that's the suite, that's the evidence. They're going relatively fast, so about 8, 9 to 10 days a day each, so we have 2 parallel streams. Then in September we will start another 2 streams. Then we have 4 streams running. The reason why we're not running them yet is there's 3 reasons. First of all, we need to have the Aura S6 initial stage, which is being produced at the moment for the back extension. We already have it for 2006. We also do, we are still working on the reprocessed data. So all the ones that are in gray, we are already in place, but the ones in red we're still working on. Then we will run 4 streams at the same time. So if these first 2 streams are done, then we can start another 2 streams. That will probably be about September 2027. Add more satellite data. And then finally, in November 27, thereabout, we will do the last 20 years, and then we will have something like from 1947 until near real time. Good. So let's look at some cases in what we have already produced now. So that's really version 1 now. It's not test data, it's just the real thing. Good. So there was a storm Egon in January 2017. It developed quite rapidly. It was quite a small-scale storm, and that's really where you can see that a higher resolution of Era 6 is very beneficial. Because if you look like at global maps and things like that, the Era 5 and Era 6 are very similar. But when you start to look at details where it matters, extreme cases, that's really where Era 6 has the edge. So the highest gust was around Dieppe, was 89 miles per hour. And they actually had to shut down part of a power plant because there was some electricity was knocked out by the wind. So yeah, so there was quite an impact. The storm is small scale, so there is the damage is local, but it was 200 million. And you really see that Era 5, Era 6 almost has the same value as an 89 miles per hour. You really see that it's more extreme. You see that here happening now. Good. Then, if you look at the waves for the same, the ocean waves for the same case, that for Eagle, because it was very rapidly, the waves couldn't really grow. But now focus on the resolution. So Era 5 was the resolution of the waves was about 40 kilometers. Era 6 is 40 kilometers, and it's a massive difference. Now we have a proper channel, but also you have a little bit more extreme waves. We have waves up to about 11, almost 12 meters in the North Sea for this particular period. Okay, another case is this is the resolution, and it's not only Europe; it's for the whole globe. Okay, we do the whole globe. This is a relatively small part of the world, important part of the world, of course, but it's not the whole world. So let's go down to the other side of the world, down under, and have another case. So this is 25 of March 2017. Let's focus on SST and ocean currents, because Era 5 doesn't have ocean currents. Era 6 does have ocean currents. In Era 5 we used, we prescribed the SST. It varies only once a day. It was based on Ostia. While in the Era 6, the SST that we used was the ESA CCI version 3 SST product, which was ingested as an observation in the Aura 6 reanalysis, and that then created, that transported into hourly fields. And then you can see on the left-hand side, you really see that the daily cycle in the SST, which we don't have in Era 5. So really, the ocean atmosphere processes in Era 6 are much more realistic than they are in Era 5. But there is a little bonus there. If you look at the bottom left, then you see a little bit of blue appearing there. And that's because there was an extreme, that's why I chose this case, there was an extreme tropical cyclone Debbie. So winds were about 120 miles per hour, so Era 6 doesn't reach that. But you can really see that the tropical cyclone, it extracts the energy of the sea surface temperature. You really see that happening. And also the ocean currents, or even ocean currents, which are being induced by the tropical cyclone. So again, Era 6 is much more, realistic than Era 5. Okay, more and better observations. So Jörg showed one plot, but we have many examples of all different satellites that we in different periods that we have been testing together with EUMETSAT and with the Spatia consortium. And it's the general picture where you add those data, you get blue, 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 blue. So it improves the analysis. I'm not going into detail. And then finally, we have the in-situ observations. So last week, there was a new version of the land data set published, and version 3 rather than version 2. And 3 billion additional observations were added. That's really a big number. 3 billion for in situ. That's a lot extra, which we didn't have in Era 5, which we will have in Era 6. And that will improve the quality of the reanalysis as well. Good. So, summary, outlook. Era 6 is in production. We have 2 streams running at the moment. We will start 2 streams in September. We expect that 2007 onward will be public by late 2027. And we might make available some test data because of the GRIP2, quite some things are going to change and people have to adapt about how to retrieve that data, how to work with that data. So summary is higher resolution, 14 kilometers, based on additional 8 years R&D. We have an ocean component, although we get the data explanation done by the Aura 6 reanalysis. It has enhanced realism. We have make use of more and better observations and resolve several Era 5 issues. Also, we have more products. We have ocean fields, height levels, more parameters. Everything is a GRIP2. We have an efficient way of accessing the data, polytope, and we have daily month statistics. And just the last remark, just an example of enhanced realism. I already mentioned the ocean currents and the daily variation of the SST. This plot here was generated based on a prototype of Era 6. That is how MTC would have seen would have seen the Earth according to Era 6 if it would have been available, because this was made for a date in 2006, which was one of the spin-off years we had. And so it looks really realistic. But if you really look carefully, there is the black spot just over Central Africa, that's a solar eclipse. Era 6 also takes account of solar eclipse. Just an example of of the enhanced realism of Era 6. Thank you very much for your attention.
Thank you, Hans. I think in this case, not respecting the 7 clubs was allowed, because the achievement of Era 6 for me are really sensational and particularly significant. We have run an assessment, a socioeconomic benefit assessment of Era 5, and the return of investment for Era 5 was something as a minimum of tenfold. I'm sure for era 6 will be higher than that. So thank you for that. I promised to give you the floor for one quick question, but I skipped the last two just because we are running out of time. Now we have times for a couple of questions before going for... I see, Anka, you are desperate to ask a question. Anka has the floor. No, you can take it from here.
Thank you. It's a short question for Hans. You mentioned running streams 10 years long, if I heard you right. Do we know what to expect at the point of concatenation between two streams that come consecutively? Is there a risk of discontinuities? That's what I mean.
Tradition.
Well, we have quite some experience with that in era 5 where we did the same. So in the troposphere, it's all very smooth. But there where you have can have problems, and where we had problems in era 5 was at soil moisture. So that will be improved in era 6 because we have this from the C3S project, this one integration of 1939, which is continuous. We initialized from that, while era 5 was initialized from era interim, and at some point even for era 40. That it gave big jumps because also the service model had changed dramatically. So and the other part is in the stratosphere, particularly humidity. And but we have to see how I think we will do much better in era 6, but we have to see how that goes. But so basically, it's mainly the stratosphere, humidity, and soil moisture where we know that these things have a long history. And where we could have jumps, but in the troposphere, no, I don't think so.
Thank you.
More questions? I know you're desperate for coffee. There will be coffee. But I think there is still space for a question or two. I do have a question for Barbara myself, because in a sense you have presented this new setup whereby more observation are available. To the user, more in situ observation. What do you think will be the next frontier? Now, also in the presentation at the beginning, we mentioned observation playing a bigger role now in the machine learning dominated world. So what do you think will be the future of in situ observation in this setting?
I think it will be important, but the problem is the financial situation and the need of some med services to think about reducing their in situ measurements, which might lead to some reduction in the available data again, which of course would be bad for all those products based on those.
Hans, Jörg, do you have a view on the matter of observation for machine learning, how the landscape may change?
I think we are in the very beginning of this, no? So I think we have started experimenting in the context of this AI DOP for weather forecasting. So if more data would help more, so at that level we are, so extend from 10, 20 or 30 years of training data, so it looks positive, but how complete that is, and if this could beat what you get out of a reanalysis, I don't know. The future needs to show that, no? It's very complex to take decisions of how you would continue with another reanalysis. No? For observations, I think it still remains important that, and this is what we would always do, you produce in the first place a level 1 data set that is as good as it could be. No? So this has been proven by now. No? It's not like you throw anything in as it comes out of a real-time machinery and it helps you. No? So this people were thinking, but this isn't true anymore. No? So that is that's what we know now. But still, you need a major transition for forecasting into real time, and what that means for reanalysis or for an analysis quality, I'm not so sure of. No? So that is, people need to demonstrate that. No? So, but maybe we learned that in COP3. So that is yes. That's the hope. But the observations is the impact the same for machine learning than it is in a data assimilation framework? Some parts will remain, some others may change. But the tools to say that for machine learning are not ready yet. No? So this would be good to know, to set priorities of what you would address. No? But I think historical observations, as we have not worked them up all, will still remain important to be included in both type of approaches. No?
Well, the preliminary result with AI DOP seems to suggest that the curation process of observation add value there as well as for traditional reanalysis. So it seems to be a low-hanging fruit. So that the activities we are doing in rescuing the data and curating the data, this will stay. I don't know, Hans, if you have a view on how, what are the new requirements coming from the machine learning and AI in terms of observation, if any, for reanalysis?
Yeah, that's a difficult question. So, so for machine learning AI, so at the moment, we have a machine learning all over the world, AI revolution at the moment, also in weather forecasting, and we have at least WF has been really proactive there. We now have our AIFS, and we have also our ensemble, but we have many more products, but they're all based on on reanalysis, for instance, ERA 5. The next step is now also really to do so they still need a physical model because ERA 5 has been produced by using a physical model and a data assimilation system. But now we're also looking in whether we don't need that model, whether we can go directly from observations to forecasts. And actually one of the ways of doing that is to go from observations to observations. So there's no model in the equation anymore, so you just train. So you have an observing system, and then you try to predict the observing station in a future state. And yeah, so that's called AIDOP. But there, of course, you can only, in other words, where you have a radius on data, say, that gives temperature as a function of pressure, you say, well, I only have a radius on data in the Northern Hemisphere, but you can, at will, you can put that radius on at any location, and that's how you can then create a reanalysis. But of course, that's only for the observations that you observe. So you need to have you have to have the observables. So it is important, I think, that in the future, satellite data are very important because they contain a lot of information, but the in situ is also extremely important because that provides the physical observations which you need for your training. So I think that gives another case that is situ, so also being that's reference data, but that is another case for in situ that's really important with going in that direction.
Thank you, Hans. I'm fascinated by the topic, and I will continue to speak about it for the rest of the afternoon myself, and probably I wouldn't be alone. But we had 5 talks, and I think we need a coffee. So I would like to ask you for the last time, 7 claps to thank our speakers. And just before you do that, just to signpost a panel discussion tomorrow, which will cover some of this topic a bit deeper. So we have space to discuss it. Now, poster and coffee break for the next 15 minutes. 7. Thank you.
pimps in the crib, ma, drop it like it's hot. Drop it like it's hot. Drop it like it's hot. When the pigs try to get at you, park it like it's hot. Park it like it's hot. Park it like it's hot. And if a nigga get an attitude, pop it like it's hot. Pop it like it's hot. Pop it like it's hot. I got the rollie on my arm and I'm pouring Sean Don and I roll the best weed 'cause I got it going on.
I'm a nice dude with some nice dreams. See these ice cubes, see these ice creams. Eligible bachelor, $1 million boat. That's whiter than what's spilling down your throat. The phantom, exterior like fish eggs, the interior like suicide wrist red. I can exercise you, this could be your phys ed. Cheat on your man, man, that's how you get a his head. Killer with the B, I know killers in the street. Still to make you feel like you're chilling in the heat. So don't try to run up on my ear talking all that raspy shit. Trying to ask me shit. When my niggas feel your best, they ain't gon' pass me shit. You should think about it, take a second. Matter of fact, you should take 4B and think before you fuck with little skateboard P.
When the pimp's in the crib, ma, drop it like it's hot. Drop it like it's hot. Drop it like it's hot. When the pigs try to get at you, park it like it's hot. Park it like it's hot. Park it like it's hot. If a nigga get an attitude, pop it like it's hot. Pop it like it's hot. Pop it like it's hot. I got the rollie on my arm and I'm pouring Sean Don and I roll the best weed 'cause I got it going on. I'm a gangster, but y'all knew that. The big boss dog, yeah, I had to do that. I keep a blue flag hanging out my backside, but only on the left side. Yeah, that's the crib side. Ain't no other way to play the game the way I play. I cut so much you thought I was a DJ. 2, if it, 1, yep, 3. SC and double O, P, D, O, double G. I can't fake it, just break it. And when I take it, see, I specialize in making all the girls get naked. So bring your friends, all of y'all come inside. We got a world premiere right here, not get live. So don't change the diesel, turn it up a little. I got a living room full of fine dime bristles, waiting on the bizzle, the dizzle, and the shizzle. G's to the Vizak, now ladies, here we guess up. When the pimp's in the crib, ma, drop it like it's hot. Drop it like it's hot. Drop it like it's hot. When the pigs try to get at you, park it like it's hot. Park it like it's hot. Park it like it's hot. If a nigga get an attitude, pop it like it's hot. Pop it like it's hot. Pop it like it's hot. I got the rollie on my arm and I'm pouring Sean Don and I roll the best weed 'cause I got it going on.
Prada dress or your Gucci bag, whether polo jeans or a doobie bag. You hold the door, alright? We coming through, try deep, hold it down for the night. Big Moo got the fifth, D like we got the Willie and girl, you got the kid. Turn it over the page, usher in all of y'all to a brand new age where status really don't matter. Everybody get right to the pitter and patter. Come on, make a move, setting precedence. It's a bigger residence, the whole scene is decadence. And the feeling is true. I'm seeing feet in my crew, you seeing black and blue. So let's go for the ride. Have yourself in tight, and if you pull the fire, breathe and stop, house, and give it what you got. Yeah, she's mighty, mighty, just letting it all hang out. Breathe and stop, house, and give it what you got. I like you to stack, that's a fact. Ain't holding nothing back now. Give it what you got, she's making it hot. Give it what you got. Millennium on your mind, are you running out of time? Hope you're skipping every line, cause I'm getting mine. Move it around a bit again. Every block, every town, we starting the trend. High mountain toe to toe. Who concentrating on killing the show? Penetration is medically slow. Mountain high, valley low, gonna find the dough. For my peoples, no matter the creed, we gonna satisfy the urge and discover the need. You feel the bite in this. If you think I'm type real, then invite me this. And let me say a rhyme in your ear. Dancing close, you the most, and you fitting here. You feel the rhythm is right. You know this fitting is tight. You think you won't, but I see you right. Breathe and stop. House. Give it what you got. Just she's mighty, mighty. Just letting it all hang out. She's a bread. Breathe and stop. House. Give it what you got. Like lady stack. That's a fact. Ain't holding nothing back. She's
Pushing on, pushing on. Yo, watch that for right. Let me get down there. Right the disco track. Let me get down there. Yo, watch that for right.
We're just chillin', moving to the funky sound. We don't need no Good. Now I'm on. Welcome back. I think we wait 1 minute more because people is coming slowly from the coffee break. Thank you.
Thanks a lot, Chiara. Yeah, so this title says the new Copernicus Pan-Arctic Regional Reanalysis. Actually, I had a presentation in the C3S General Assembly last year, so also OCARA 2, but that was case studies, some early results when the system was still in production. So what's new now is that we have completed the 40-year time series of OCARA 2 data. So who we are a team led by Met Norway, partners from the Nordic Met Institute, Meteo France, and Danish Geological Survey. We are, of course, part of C3S. We are doing a 2.5 kilometer regional reanalysis over the Arctic using ERA 5, 32 kilometer resolution on the lateral boundaries. So just before I start going through OCARA 2, just some background, the Arctic amplification backdrop. Why is it interesting to have a regional reanalysis over the Arctic? So this slide shows what you can find in climate projections. This is actually average of 33 CMIP6 models from the previous CMIP with an intermediate climate scenario. And to the right, you see the average of these models in temperature change from pre-industrial until the end of this century. So you see there's a maximum in the Arctic, which is more than 10 degrees warming, compared to, for instance, Western Europe, where it looks like it's about 3 degrees. So, and you see also that the warming varies in space in the Arctic with these Arctic amplifications. There are feedback processes, complex physical interactions between atmosphere, ocean, and cryosphere. So these are connected to important feedback processes causing this Arctic amplification. So this is what you see in the climate projections. And if you look at what was in the recent European State of the Climate reports, there were some plots also highlighting this. So this is from ERA 5, showing what has happened recently, actually data from the last 30 years. So from the panel to the left here, you see that the Arctic in the last 30 years, the warming rate has been about 3 times the global one. To the right, you see the spatial, quite complex picture. It's similar to the one you see from the climate projections, but with some more regional variations, which is natural since these are real observed data and not average of many climate models. Highlighting things like Svalbard is one of the fastest warming places on the planet. And you see this hotspot in this area in north of Siberia, where you have quite strong warming. So the quite strong warming processes going on this. That's part of the background why it's interesting to look in more detail into the Arctic. So now a little bit about what we have been doing in terms of regional reanalysis in the area. We started with this CARA 1 contract, which consisted of 2 domains, the CARA West and the CARA East domain in the European sector. So this has been completed with the data set starting in 1990. And for that, we are now doing monthly quasi-real-time updates of the reanalysis. So, and this will go on until March 2027. Then the updating will then be in the CARA 2 area. So this is the next generation, same resolution as CARA 1. Last week, this was released in the Climate Data Store. So we have 40 years, starting in 1985, ending end of last year. We had the partial release of some time slices December last year, so it has been available some time, but complete only now. And in the future, we will start with timely updating, monthly updates of CARA 2. So in a period from November 26th until March next year, we will do
updating of both Cara 1 and Cara 2, and after that we will only update Cara 2 on a monthly basis. And I should also mention that there's a machine learning effort that will be presented tomorrow by Eivind Støylen on also making a kind of machine learning emulator of Cara 1 and also of the European reanalysis SARA, so that's also something that's been looked into. So for this, we have done quite a lot of adaptations to the Arctic. So what's, physics of the atmosphere is the same as anywhere else in the Arctic, so the NWP models are similar, but there are some challenges illustrated in the figure to the right here. You have parts of snow cover, you have glaciers, you have sea ice, so you need to do some, be more careful in some aspects of the modeling. Something more demanding in the Arctic, and that's describing these cold surfaces that we have. That's not always very well described in global system. So it's also a fact that the Arctic is more observation scarce, so you need to have schemes that are adapted to that, at least concerning conventional observations. Of course, satellite coverage from polar orbiting satellites are quite good, so we need some extra care here. That concerns surface schemes, sea ice schemes, snow on sea ice, handling of glaciers, glacier albedo, snow scheme, things like that. We have been working a lot with. We also need to adapt dedicated data sets to get good information about the surfaces with high enough resolution when we run 2.5 kilometer model over this large domain. So we have quite a few specially prepared data sets from that, and we have also collected extra ground observations from local observing programs that has not been routinely shared earlier. Yeah, and of course, Cara 1 and Cara 2 both build on experience from operational Arctic NWP, both in Denmark, Iceland, Greenland, and in Norway. So these are some examples of the high-resolution data sets we have been using and adapting for sea ice and sea surface temperature, for satellite snow data. We have been working on correcting physiography, but the databases are usually much worse in the Arctic than other places, and we're also looking into historical satellite data for glacier albedo. So we've done a lot of evolution from Cara 2 to Cara 2 from Cara 1, quite a lot of effort to be able to make the system run on such a large domain, which we have never run on before, so that was quite a lot of effort. We did optimize model numerics using single precision in parts of the code. We used hydrostatic assumptions. So our system can be run both hydrostatic and non-hydrostatic, and it turns out that actually there's not much difference between the two. We get exactly the same performance using hydrostatic approximation. So then we save some computation time. We have 40 years. We do some updates in the model formulation, in the surface scheme. We have a new physiographic database. And of course, the most important thing is the large extension of the domain. So what was released now was this time series, 70 variables, surface fields, 2 subsurface layers, 65 model levels, 23 pressure levels, 11 height levels, and some new features with geographic subsetting, providing daily, monthly means, as Hans also showed was included for ERA 6. Some use cases. We have some requests from users. This is just to show what type of use we have. This is from a previous user workshop, just indicating people's field of interest. So a lot of the interest comes from the climate change and climate change monitoring community. There's also something on forcing on downstream model, energy application, extreme events, machine learning. That's probably much higher now. This was a few years ago. The climate data store, most of the requests are from research and education, according to the classification used there. We also have got quite a lot of requests from research on glaciers and also on permafrost research. So this is to show, this is a picture to the right from European State Oil Climate Report, so showing that glacier modeling, you really need quite a lot of small scales to capture the glacier arms, etc. So glacier mass balance modelers need atmospheric forcing, and they are requesting Kara data to capture these details. We have also got requests from permafrost modelers. Of course, that's one of the important feedback mechanisms in Arctic, the thawing of the permafrost. The figure on the right shows for different areas how the measurements of what we call the active layer is evolving, or has evolved recently. That's the depth of the permafrost that thaws in each summer. And they are also requesting Kara data because they need high horizontal resolution and they need forcing on the surface. And they run dedicated models for this, even if Kara has a good representation of the surface. So how does Kara 2 differ from ERA 5? These are mean absolute differences. So to the left, you see for temperature, for winter seasons. So actually you see quite a lot of differences between the North Pole and the Bering Strait, and we believe this comes from that we use a more advanced sea ice surface scheme with the ice thickness and evolving and snow on the sea ice. So we actually have some evidence that what we see in Kara here is better than ERA 5. Also see differences in temperature in areas where you have terrain, where you have strongly varying topography, and you also see something in the forest areas in Siberia and Alaska, which is probably not necessarily so good thing for Kara because it has to do with the way 2-meter temperature is represented over forests, which is a bit different from how ERA 5 represents it. To the right, you see the same for wind speeds, and there you also see very strong features connected to topography, to coastlines, to orography, where we resolve more detail in the Kara. So we believe that we add quite a lot of value there. So looking a bit more into details, how do overall verification statistics look, local climate statistics? I said something about capturing of extremes last year, so I won't touch that, and a little bit about climate trends. Yeah, so this is some summary verifications against observing stations for ERA 5 and Kara in terms of degrees differences, RMS differences. So for temperature, you see that Kara is always quite a bit closer to the observations than ERA 5. You also see the same thing, but not so big differences for wind, but the differences depend on region, season, and parameter. So generally, in terms of summary verification against observation, it looks quite good. You can also look at climate statistics distribution, and there I selected the station at Svalbard. This is one of the stations where you really see big differences in the histogram for the statistical distribution of wind speed, where you see that this high tail in the observed wind speed that you have at the lower left, that you also find in the Kara wind speed, but you don't get it in the ERA 5 wind speed histogram. On the top for temperature, there are some differences, but not that dramatic. Maybe Kara is a little bit better. You can also look into the tails of the distributions to look at extremes, which are quite interesting, quite a lot of applications for. So we also see some differences there on the tails. If you look into the temperature trends, we now have, since we have the full time series for 1986 to 2024 for Kara, you can look into how does Kara 2 differ from ERA 5, and also here you see, okay, there's quite a lot of similarities. You have this hotspot north of Siberia to Svalbard that you have I've seen in these early plots I presented also from the climate projection models. What we get is we get a little bit higher maximum warming in Kara than we get in ERA 5. And we have some supporting independent observations for that also, that Kara actually, that the warming in observation is really closer to what we see in Kara here. We have some independent Russian observations and Franz Josef line confirming this. We also see that we have a little bit more warming in Kara, warming trend between the North Pole and the Bering Strait. And we also have some evidence from satellite surface temperature measurements and buoys. And we believe that this is connected to the sea ice scheme that is a bit more advanced in Kara than in ERA 5. Yeah, so overall, we think there is some improvement, some added value there by having this high resolution system. So the Arctic undergoes rapid climate change. So reanalysis for monitoring and studying Arctic change processes are increasing relevant, especially for the feedback processes. For instance, for downstream models for glaciers and permafrost. And there are quite a lot of applications that are not gone that much into here. Machine learning is one big upcoming item, of course. Engineering applications, extreme events, renewable energy is coming. And in many of these applications, high spatial resolution is requested. So Kara 2 builds on Kara 1 with adaptations to run on a large pan-Arctic domain, the same horizontal resolution. It has, I don't present comparison to Kara 1 here, but the performance is quite comparable. We have quite a bit more detail on that in reports. So we inherit many properties from ERA 5, using it on the lateral boundaries, but we add value to it in many aspects. Finally, some advertising. We have a user workshop next week, so you can still apply and be registered for that. So, yeah, that's it. Thank you.
Thank you very much. Thanks for the presentation. So while people maybe still reflect on questions they can have, I have a quick one for you that is related to the presentation of Hans. So ERA 6 is coming. What could we expect from Kara 2 and ERA 6?
Yeah, so we still use ERA 5 on the boundaries, so we kind of have a handicap relative to if we had used ERA 6, because we inherit many properties of the host model. But still, what we see from, for instance, regional and NWP, that running 2.5 kilometer model actually brings quite a lot of extra value relative to, say, 10-15 kilometer model. So we see that both in extreme events and resolving local topography. So, but we will see. We are very curious about ERA 6 and compare. We will do that.
Yeah, so we are ready for ERA 6 Kara 2.
Yeah, and hope for a next generation with that on the boundaries. Yeah.
Thank you. We have a question, Stefano.
Do you use the same CIs in the two, or what happened? And you don't have an ocean
no,
assimilated, of course. You must have some sort of observed ocean or something.
Yeah, we use satellite-based twice daily data. It's very similar in Kara 1 and Kara 2. But we do a merging of many different data sets for the CIs, because we also rely on navigational maps for some aspects.
So there are differences between the two CIs?
Because we have to extend to the big Pan-Arctic domain, and we need a consistent product all over, so we did some minor adjustments, but they're quite minor actually.
Thank you.
Yeah.
Thank you. Other questions? No? Okay, not really. Maybe I have another one for you, if you're happy to stay on stage one second.
Sure.
So it's quite exciting, I think, the Kara 2 product for the monitoring of the Arctic region and the Greenland. No, it's very strategical, and not only because of the strong climate change signal, but also because of this geopolitical competition in this area, but also emerging economic opportunities, you need transport, and so on. So what do you think that Kara 2 can really make the difference in this respect? You mentioned something in your last slide around the application, so in thinking of policy-relevant metrics, I don't know, extremes, temperatures, shift of precipitation, compound events.
Yeah, I mean, we have some experience at Met Norway in guiding people operating in the Arctic, and I mean, there are quite much stricter constraints, because infrastructure is much more sparse, search and rescue are much further away, so you really need to be more careful with many things when operating in the Arctic. And then, of course, the combination of ocean and weather and sea ice condition is what people need to be prepared for. So Kara gives information about much of this. So I think that will be a help that they can get climate statistics and
Thanks a lot.
knowledge about extremes. Yeah.
Thank you.
Okay,
Thank you,
thanks.
Harald. There's another question. Yes, we can move to the next speaker. Okay, we have now 3 ECNWF colleagues that will come on stage. So the first speaker is Eleanor Hansford. She is a scientific officer at ECNWF. She works as technical officer for the ECV program. She works also in the climate intelligence team, and she helps with the European stage of the climate and other climate intelligence activities. And so she presents today about satellite data, so from satellite data to decisions, building trust in C3S ECVs. Please, Eleanor, the floor is yours.
Hi, so I'll start by, it's hard to see everybody. I'll start by saying that I'm very pleased to be able to talk to you all today, especially when everybody's so fresh-faced despite all the possibly delayed flights, etc. So just to introduce myself, I'm Eleanor, but you're welcome to call me Ellie. I work at ECNWF as a technical officer on the ECV program, which is headed by Joaquin Munoz, and also involved are Eric Lobel and Joao Martins. Today I'm just going to take you on a nice, gentle journey to talk about how we build trust in C3S ECVs. So I assume everybody attending here knows what C3S stands for, but possibly not everybody knows what ECVs stand for. So just in case, ECVs stand for Essential Climate Variables. If you want like the textbook definition for them, they are the physical, chemical, and biological properties or variables needed to characterize Earth's climate and its change. We follow the GCOS framework, the Global Climate Observing System framework. And under that, we currently offer 32 out of 55 ECVs using satellite data, which, I mean, I'm biased, but I think that's quite impressive. And what that means is that we have a lot of CDRs, so climate data records, and these are long-term, consistent, quality-controlled data records. And these are usually produced in initiatives like ESA-CCI, which is the Climate Change Initiative, and they do like the underlying science and produce the CDRs, and then we bring them into operations. So we enable the continuation of the time series, doing things like producing the interim CDRs, the ICDRs, and also enable periodic reprocessing, etc. So I think from this, everything's looking pretty good. So what's the problem? And really, like, there is no problem. There's just kind of a happy challenge, if you will. And that is that we have all this great data, but how do we get people to trust it enough to use it when taking decisions? And I think really the key to that is kind of anticipating the kind of questions that users are going to have. And these are users like across the board, so from policymakers to researchers to just really curious members of the general public. They are likely to have questions like, how is the data produced? Is it of sufficient quality, i.e. kind of, is it good enough? And is the data set suitable for my application? So with that in mind, I'm just going to take you all through the kind of processes that we have to try and build trust in the C3S ECVs. So I've called it the ECV pipeline. I'm not sure that name's catchy enough to stay, but for now, it's going to have to work. And also it looks like 4 pipelines, but it's actually left to right, so it's just one. And it obviously starts with the data providers, and who unsurprisingly provide data alongside documentation. And then this goes for external expert review. And then once they're happy with it, it goes to ECMWF. And then once it's been integrated onto the CDS, the EQC function can begin. And you maybe can't see it right at the bottom. EQC stands for Evaluation and Quality Control. So all I'll do now is just go into each of these ones a little bit more. So the data providers, as I've said, they provide data. And they also provide these 3 key documents, which are really important because they go up onto the CDS along with the data. So each one tries to answer one of these kind of key questions. And again, a few more acronyms for you. So we have the ATBD, which is the Algorithm Theoretical Basis document. That answers the question of how is the data produced? And that's kind of the scientific and algorithmic basis of the product. And that will talk about like input processing steps, the underlying theory, etc. Then we have the PUGs, which is the Product User Guidance Specification. That answers the question of how should I use it? This is a really nice, like, non-specialist guide to just kind of help people get into the data. So that contains practical guidance where it describes like the variables, the formats, the access, etc. And then last but not least, and also possibly most important in the context of this presentation and presentation block, is the PQAR, which is the Product Quality Assessment Report, and that tries to answer the question of, can I trust it? So you can see why it's important. And that's really just an assessment of the data quality, where they describe the validation methodology, the uncertainties, and obviously the results, etc. And so once the data's done and the documentation has been provided, it goes off for external expert review, which is pretty self-explanatory, really. It is reviewed by experts who are external, and they do like a quick sanity check of the data itself, but also probably possibly more important in the context of this is that they provide reviews against the sort of the 7 dimensions that they use here, and they also evaluate the documents against the EQC user requirements, which helps the EQC function further down the line. There is often at this stage quite a bit of back and forth between the data providers and the reviewers, sometimes with regards to the content, sometimes with regards to following the templates, etc. But once they're happy, it's good. And it goes off to ECMWF, where it is reviewed by a technical officer, so somebody like me and a couple more people in the audience and online. And the technical officer will kind of review the recommendation for approval, have a look at whatever is up for approval, and kind of often initiate discussions with the reviewers and with the data providers themselves, sometimes doing also like a little bit of mediation between the two, which is also good and interesting. And then once that's done and the technical officer is happy, it gets approved, it can be integrated onto the CDS. So perfect. So in that sense, you could say, well, it's done, it's available, and we have the documentation. So, you know, it's good to go, isn't it? And in some senses, yes, but in other senses, it's highly valuable to provide for users kind of another layer of synthesis. Yes, we do have all this high-quality data and some rigorously reviewed documentation, but in some ways, it's for a lot of people who are, you know, often quite time poor, etc. It's really valuable to provide kind of succinct, clear statements about quality that users can kind of check and take action on. So in that sense, that's what EQC exists for us. EQC, as I said before, being evaluation and quality control, independent external evaluations of data on the CDS, and it's really important for transparency, as you can say, and obviously that's core for building trust. So there's kind of 3 pillars that we have to EQC. We have the quality assurance pillar, and that kind of checks for compliance with data requirements. These are shown on the CDS as like little tick boxes on the right-hand side of the CDS entries. And they kind of just look at things like, is all the documentation there for each version? What about metadata? What about accessibility? And quite a lot on versioning, etc. And that's, as I said, that's presented as interactive checklists. Then we have quality assessments, which are really interesting if you enjoy that kind of thing. They look at a specific quality attribute in a specific use case. So the attributes, for example, being accuracy and precision, or uncertainties, or spatial and temporal resolution. To provide an example, there is one for LAI, so leaf area index, and it looks at spatial and temporal completeness to see if it's sufficient to look at drought over China in the late 2000s. These are presented as Jupyter notebooks, and they're really nice because all the code is therefore like reproducible, etc. And then lastly, we have fitness for purpose. I don't know if it's weird to have a favorite EQC pillar, but I think this is mine. This is just because it has its own tab on CDS. You'll see like overview, data, and then you have quality. And in there, then you have the fitness for purpose. And that's really nice because it just describes it's just kind of bulleted points that kind of discusses the strengths, the limitations, the uncertainties, and the sort of recommended uses. And so that's really easy kind of takeaways for users. So again, this is all looking great, but is it great? How do we know it's what users want? Well, fortunately, we've gathered some feedback, which always helps. So this is kind of a summary of the feedback we've had on EQC for ECVs. I think one thing I really liked personally is I've put some at the bottom, is seeing some of the use cases, because I think sometimes it's easy to think about, where, who is actually using this data, because if you're on one side, you don't always sometimes see the other side so well. And so you can see here some are exactly what you expect. For instance, somebody is using the fire burned area data to look at wildfires in Portugal. Okay. Somebody else is using satellite data to look at sea level change in the Caribbean, which is also what you'd expect. And then I just like the ones that are a little bit more interesting, where somebody is interested in primates and they are looking at the food, the kind of the habitat suitability for food of gorillas in Rwanda, which I think is really interesting. But I think the main things to take away from here are probably the nice big numbers that you can see on the screen, and they show just generally that people are either satisfied or very satisfied with how the EQC for ECV is at the moment. So a lot of people are happy of how you find the information and how it's displayed, and fortunately they're very happy that the quality information is sufficient, which is always promising. And there's a lot of, they're very happy as well that there's, the information is quite clear. So just to kind of talk about that, because again, that's looking like everything's looking very positive, but I mean, we're not sort of resting on our laurels about that. I mean, I am, because I'm not involved in it, but I know that they've signed the contract now and had the kickoff meeting for using, as you'd expect, AI to improve EQC. And I believe they are doing something like using large language models to kind of make EQC more dynamic. So you'll be able to do natural language queries, and you'll be able to have data summarizations, and you'll be able to get tailored recommendations. So I think things are looking even brighter in the future. And so, yeah, that was just a little summary of all the kind of steps that we have involved in how we're trying to build trust in C3S ECVs. And I think that's everything. So, yeah, thank you.
Thank you, Ellie, for the presentation. Thank you, yes, for these details about the quality and the review process. Sam.
Thank you. Great presentation. On your last slide, you had, besides the amazing statistics, you had the bubble plots on the left-hand side, with the largest bubble being data literate users. Has there been discussion amongst the broader teams of how we increase the size of the other bubbles? And so it's great that the current users that we have are really satisfied, but how do we increase the number of users leveraging this satellite data?
Yeah, that's a really good question, and I think really valuable, because I think it's really easy to alienate people. I mentioned earlier when I was talking about people that try and take people looking to trust the data to take decisions, and also, you know, some of the users being people with like curious members of the general public, etc. And that includes, and also, it's not just about, you know, research and policymakers, it's also about master students trying to get research projects done, etc. And I think probably one of the really important, or like two of the really important things we're doing at the moment is we've currently put out an ITT about making an ECV web application, which is going to hopefully make the data much more accessible to people. It's going to be very fast. It's going to use Arco, so analysis-ready cloud-optimized data. It's going to give people really easy visualizations, and it's going to really hopefully allow people who aren't necessarily super computer proficient to play with the data very nicely. And the second thing we're doing, which is a little bit more under wraps, is we are also developing what we call the CI like the ECV CI dashboard, so climate intelligence dashboard. And there we're working, which I think is really great, is we're working directly with the data providers to come up with. So we're developing the website ourselves, and then we're asking their input to produce what we think is the most useful plots for each variable and each product even, which is great because we're going to offer it at different levels of information. So we're going to have kind of at a glance for people that are, you know, really just to say not into climate data at all. We're going to give them like very simple overviews, and then we're going to have in more detail, and that'll be a little bit more scientific based, and then we're going to go even further into like the third tier, and that will be for people that really kind of know what they're looking at, and that will give people a very nice, hopeful kind of multi-level overview of ECV data.
Yeah. Great. Other questions? Yeah. One in the back.
Yeah, thank you very much for the presentation. You mentioned about the AI for the EQC. So for your feeling, how much you can give to the AI of the whole EQC process?
Do you mean what are we going to provide the AI with? Sorry.
No, I mean, because most of us using AI nowadays. I mean, and have feeling about how much it can do. So what do you think, how much it can do for the EQC?
So I am unfortunately not the best person in this room to talk about, but I can definitely introduce you to him for that. But from what I've read, I think it's going to be quite impressive. I think it's, as I said, it's really going to make things more dynamic, and things like getting tailored recommendations for data. You know, in that sense, I think people are going to be able to put in their use case and have recommended data. I think will be really valuable to people. And I think that level of kind of, instead of having to hunt through various data sets to find the right information, instead of, they'll be able to ask something like the knowledge duck, and they'll be able to look at that and say, oh, you know, I want to do this, and it will be able to feed it to them straight away. So I think hopefully that should really help uptake of data for people that otherwise just kind of don't really have the time to trawl through all the various entries. So I think if it's used well, and I think it will be, and you know, it looks very promising, as I said, I think it should be really valuable.
Other questions for Ellie? No? Yes, one. Sorry. We need a microphone here. Yeah.
Thank you also for a great presentation. I'm always curious when I see these survey results, and there's a huge majority with like positive because that's the safest choice. But the devil is so often in the small things, like these three people being very like negative.
Yeah.
Why are they? Do we have more information on this? And do we have a mechanism to report back to the data providers on what they could improve in their data sets? Coming from a data provider perspective myself.
Yeah. So I think this is a great question. I know that we have quite a lot of detailed feedback. So I believe that we have the information from those very negative people in order to really understand how we can improve it. Because, as you say, it's not that just people aren't satisfied, they're sort of highly unsatisfied. And, you know, they obviously feel like we're missing something quite significant. Yeah, I guess maybe they are, very angry, yeah. So I think we have that information, and I believe, as I say, we can sort of, it will go through the various channels and will eventually feed back to providers. But I like to think that, it's as you say, it's nice for a presentation to always present the positives, but looking at the negatives is possibly more important because it's really where you can tighten things up. So that's a great point.
Great, thank you so much. Thank you, Ellie. Yes, no, I think you can go. We don't have a panel discussion, but thanks. Oh, feel free to sit if you prefer. Okay, so from the satellite observations and ECVs, we move now to climate predictions and projections, and we have two speakers. First one is Anka Brukshaw. Everyone knows Anka, I think, in this audience. She has worked for about 20 years in the area of climate predictions. And since the last 10 years, she has been working at ECNWF leading on these activities. She has attended all the GAs. So let's welcome Anka on stage. She will tell us about the climate predictions and projection components at C3S.
Oh, I understand now everybody is shading their eyes. We can't see anything from here. Anyway, let me get straight to the point. Indeed, as Kara says, we've been talking about this for a while now. Intuitively, as well as from actual experience in the last 10 years, we know that people want to know about what happened in the past. They want a very good description of it, but also they ask questions about what might happen in the future. And this is a presentation, a very brief summary on how we address this topic in C3S. The next two presentations will be talking about data about the future. Again, we've presented every year. Those of you who use this data are very familiar with the setup, but I'm not going to assume that everybody here is in that situation. So just maybe a different take on the way we normally go about this. We tend to think about it, I tend to think about it in terms of timescales it covers, but here I'm talking more about what users find when they come to C3S. They will find applications and graphical products, from seasonal forecast and from climate projections, and the examples here are charts that we present for the seasonal timescales. We have been doing this since 2016 in the context of C3S, but also you might now be familiar with the C3S Climate Atlas, which is a continuation of IPCC's 6 assessment reports, Climate Atlas created for that purpose. There'll be more presentations about some of these topics next, so I'm going to just quickly go through this. The next, and a very important component of this part of the service is the data products. People do use the data, they do combine it and interpret it in ways that suit the purposes. Seasonal forecasts have been a popular data set. If I remember rightly, at the last survey, the second most popular data set with private companies. Now we've started to work more systematically on decadal predictions. Data from decadal predictions is coming soon in the Climate Data Store. These are 10-year forecasts from 5 decadal prediction systems. And finally, climate projections. Again, many of you in this room would have worked with climate projections, whether from C3S or the wider community. Last but not least, tools. Tools to allow people to make sensible use of these forecasts. We can't anticipate all needs, but we give good examples of good practice. It's a very rewarding part of the work, I think, because when people come and ask you questions about how they should do a particular type of work, you put out a workflow, they run it, they find an answer to the question, and they take it on. And they seem to be very pleased in many cases. But my colleague who's following me will tell you more about this. Now, I will go back to my traditional way of looking at things by timescales and just very briefly virtually signpost the stuff that I think it's important to remember at this time in history. I haven't put any animation, so please read it from top to bottom slowly. The C3S seasonal forecast component is a multi-system setup. Now we have 9 prediction systems. I don't think I had a presentation last year, so you may not have seen in this forum the full iconic design of the logo, but there it is. So those are the components that contribute. What we've done since last time we met, we've set up new contracts, many new contracts, by the way. I've written that on a slide. Now they include the Met Office from the UK. We missed the contribution in a fully engaged way for the last few years, but now they're back. And indeed, one of the things they've been doing since we started these contracts after last year's GA, they have updated the forecast system. So have the Japanese Met agencies institution who contribute to C3S as in-kind contributors. We have created a new graphical product. Again, those of you who follow the seasonal forecast output, you would have seen it. It's for indices, time series of indices, and we do now have a new product that will be appearing in a moment. Very soon we will be introducing a new way of referring to indicators of activity in a coupled atmosphere-ocean modes in the tropics, specifically the El Niño, La Niña Southern Oscillation, and we're introducing the new relative index. I will say relatively little about this, but if you have any questions, I'm happy to answer them. Lastly, but by no means least, we have created Jupyter notebooks as shared outputs, software outputs, to allow people to reproduce the images and the graphical products that we offer in public. And this is one of the ways, for example, users can prepare the data, download it, and use it downstream in ways that they can't these days by just, at present, by just downloading stuff from the Climate Data Store. What's coming next? Well, a couple of things. One that I mentioned last year, but it's important because it will change potentially the way we do C3S operational outputs from seasonal forecasts, and that is the upgrade of the seasonal system from ECMWF. I put here the comparison of the current system. It's called CES5 with the future one, CES6. And if you just look at the number of blue lines, you will see that there's twice, well, you might be able to count there's twice as many on the right as on the left. That is because we are going to be initializing predictions not once a month as we did before, but twice a month. And this time, unlike at present, when we extend 4 of the forecasts in a year to 13 months, each month forecast will have a smaller size ensemble that runs for 13 months. There will be twice a year initialized predictions that run for 2 years. We can talk about what we might expect to see there as skill, but not in this presentation. Now, we can't ignore the fact that machine learning techniques are out there and people have high expectations of them. The weather forecast paradigm has raised these expectations. In the longer range timescales, the problem is slightly different. It's not a big data problem, as one of my colleagues like to say. It's a small data problem. There simply isn't enough independent data to be able to treat it in the same way. we simply don't know how to do it at the moment. So I know that there are papers published out there and there are approaches that people have tried and they've proven valuable, people have demonstrated the value. But I think when you start to think about the context of a multi-system prediction service, and this is not just because we invented it like this is just something that's been going on for a good 20 years now at international level. WMO has endorsed this. It was the first activity that had a multi-system setup. What do we need to do, though, for machine learning specifically for this? Well, we need to think about what's an appropriate methodology to train machine learning models, because, as I said, we need to have independent data for verification. Then we need to think about an appropriate way to evaluate these things. It's related to this. You can't, if you evaluate things on a sample of the data that you've used in your training, then no surprise, you will get very good results. When you start to use the system out of sample, you will have a very unpleasant surprise. The whole point of this is to aim to understand whether complementarity with physics-based models adds value. So do we just switch off the physics-based models and stop and continue to use AI only? Are they going to be that much cheaper? Well, if they are, then they might offer us opportunities for large ensembles, which would lead to reducing uncertainty in products. Bottom line, all this stuff we are interested in finding out is to inform the best strategy for seasonal prediction in Copernicus 3. Then, longer time scales, I said that the new contract has started for decadal prediction. It includes several components. Some of them are very tedious and time-consuming and of technical nature. But exciting for people who want to develop downstream applications. Specifically, we are going to produce a large set of variables which involve preparation of data, quality control, quality assessment, and specifically scoping the specifics related to initialized predictions on these timescales, which are currently not covered properly by the CMIP community, Climate Model Intercomparison Project. Coupled Model Intercomparison Project, apologies. We will cover the production, we have covered the production of forecasts initialized at the end of 2025. We hope to have the data in the Climate Data Store very soon. 2026, 2027 are also part of this contract, so the contractors are expected to produce these real-time forecasts in timely fashion. We will publish this data at the Earth System Grid Federation nodes. Those are the details of the project. I decided to catch up with my colleagues on acronyms. And this data will make its way eventually in a CDS catalog used, helped by another contract. Case studies are planned, and they've all started for 5 individual sectors. Each of the partners in this project, the contributors to this contract, have one particular topic. They've identified a user, a problem, and they're trying to see if decadal predictions can address it. Now, I personally don't expect the answer to be yes in all cases. I would be surprised if that were the case. It's quite unrealistic to expect, but it's worth trying because people want to know if something's possible or not. Learning something's not possible, it's still a very valuable piece of information. But also something you might be interested in, or people online who are listening, we plan to publish much more in the way of software for repeating and extending and modifying these calculations, making it available to users and helping them tailor things to their own application. Lastly, not least, but certainly something that I can delegate to my colleague and other speakers here in a large way, is the work on climate projections. So we do have now a contract that's working on the quality control framework for data from climate projections. The plan is to support the activity so it can be used as a starting point for the quality control for CMIP 7. We will update in a catalog entry, so this is something that maybe users will not, C3S users will not see immediate result from, but certainly once the data appears in a CDS, they will benefit from it having happened. The plan is to probably this year update the CMIP 6 catalog entry. Those of you who've used it will be probably aware that it will never hold the whole of CMIP 6 data, but it will have more data. It will be synchronized with what's currently still available at CDS, but at ESGF. But as you well know, this project, CMIP 6, is behind us. CMIP 7 starting, everything's frozen. we still want to keep the data robustly checked in a climate data store, for example. We want to have consistency between the projections for the future and the historical simulations. We also will be publishing data from Codex using CMIP6 boundary conditions. That will be later this year. We have started to look into creating more information at regional levels from climate projections this time, although we are aligning ourselves as much as suitable to Codex and plans. We've decided to invest in the machine learning side of things rather than, as we did in Copernicus 1, in boosting the sample of regional climate model derived simulations. Primarily because we do want to have a more uniform coverage across the world. We know that European centers are well placed to do the regional climate modeling and projections as a result. But when you go away from Europe, the problem is much patchier, and we do have services and products that cover the whole world, and very little data of the same quality as that for Europe to use. We are looking into whether machine learning methods can fill this gap, and we will have a talk about this tomorrow, I believe. The Climate Atlas, if you've not seen it before, come and talk to us about it. There will be a presentation. There have been updates. Again, my colleague Chris Goddard will be speaking about them in a moment. And we have engaged in discussions with the working groups of IPCC's working group, teams that do the assessment report, around 7 of assessment reports. We want to continue to support Working Group 1's Climate Atlas, and also we have had discussions about whether Working Group 2 is ready for an atlas and in which way we might be able to support it at the moment. Now, before I finish, Carlo asks me every time he goes to the user forum to give him something about the prediction itself. And El Niño is probably, you might have heard 1 or 2 people talk about the fact that there's an El Niño in the predictions. I don't know if it's going to happen, so I'm reserving judgment here. But here are the maps of sea surface temperatures in the tropics. No, these are the global maps, sorry. If you know about El Niño, most of you do, you know you need to look in the tropics, in the Pacific specifically. And here are the C3S multi-system components side by side. And you see that all of them have a red patch there, pretty much in the same place. So that is not only strong predictions from an individual model, most of them say the same thing. That's one thing. This is a 6-month prediction, so the time frame here is the end of that period. But things continue to grow typically in the ENSO state up until the end of the year. ENSO events, whether El Niño or La Niña, tend to peak around the end of the year. So this is what we expect. The ensemble mean picture I'm giving you here is telling you nothing about the certainty or indeed the amplitude very much. But believe me, that is high. And here's the evidence for that. So this is, I promised you, an illustration of the new product. It's the panel on the left. So up until now, if you've looked at our outputs on the right, we have these percentile plots that show for each of the component models in a different color the percentiles. Now, that doesn't help you at all to know what's happening in the middle. Those of you who are used to the traditional plots in which you just put lines, time series, you know that we've about 400 or 500 lines on top of each other now, and you can't make any sense of them. So we created these plots. You still can't make much sense from the right-hand plot, other than to see which of the models are outliers, whether on the low side or the high side. But now we've introduced the thing on the left in which we throw our ensemble members together, having done some post-processing that makes that a respectable thing to do. And now you can see that the lines, if you've managed to read the captions, if not, the lines are percentiles 10, 25, 50, 75, and 90. And if you can see the 50th percentile, the one in the middle, exceeds 2.5 degrees centigrade. This is why the world is panicking, thinking that this is a very large event. Now questions have started to surface once again about whether given the climate change we've had, this is the fair way to measure El Niño and what does it all mean. So this is why WMO has decided to recommend for the time being the creation of a new index following some published literature. Next Monday, there will be a launch of the explanation about this new index, and from June onwards, we will produce forecasts for that index as well as the classical one. Thank you.
Thank you, Anka, especially for the update about El Niño forecast and the new index that I'm very curious to see.
That's not the
about.
only fan.
Yeah, indeed. So I think in the audience we have many users of predictions and projections, but we also producers. So I'm sure there will be questions for you in the audience, please. Sorry, because here we are a bit.
Thank you.
Thank you for dipping the lights. Somebody has dipping the lights.
Thank you.
Thank you for the presentation, Anka. I have two questions, one quicker than the other, I believe. The first one.
I'm here for the whole time, so you try your best.
First one, you mentioned that publishing the decadal data on the C3S depends on another contract. I don't know if we may have an estimation of we are discussing a few months or longer than that.
A few months, but it could be 2 or it could be 10. No, it's more like 2 months.
Okay, perfect.
Probably
thanks.
less than that.
And the second one, on the discussion on the usage of AI on seasonal, I don't know if part of the discussion is where to use it in the sense of in part of the production chain or as post-processing / downscaling generation of products. If in projections we are discussing a global approach to use AI to generate additional information, I don't know if something similar could be...
I think I understand your question. I'm going to answer what I think I understand anyway. It is for the production part. It's not for the post-processing part, at least this piece of work. And I'm saying it with sort of in a tentative way. So currently, this is a plan to put it forward to propose launching an ITT for this. We know there are groups out there who do production of seasonal predictions using machine learning techniques. We know there's a diversity of techniques, and actually we want to go after diversity to see if, like in the GCM world, diversity adds value. If everybody uses the same data set and similar methods for deriving them, you don't expect to get very different stories. So that's the, but again, when we publish, that's the explanation as to why we want to do it and what we want to achieve. We want to understand how you do predictions in order to get something useful out of it.
Okay, thank you.
Any other final urgent question, given that you have the opportunity to have Anka here in person? Okay, if not, let's thank Anka. There is a question. Sorry.
It's a question on observation. So from my past, I remember that these tau buoys in the Pacific were pretty important. Do you see, is there any decay and how that impacts your prediction?
I think it's too soon to tell, but for a proper, complete answer, I'd have to refer you to my colleagues who do the initialization. The initialization for seasonal is done separately from the, or it's a flavor of the NWP initialization. But you're right that it matters. You need to use data that has some continuity in time and homogeneity, because you do need to use the information you have about the model climatology by running hindcasts to correct errors in the real-time forecast. So it's crucially important to have a homogeneous data set. I can't remember what we use for the ocean. I know for the atmosphere we use ERA, and hope that the sort of operational analysis in real-time mode matches that. But yeah. I can get back to you.
Thank you. I think we can thank Anka again. And we welcome on stage Chris Goddard. Chris has a background on climate services. He works at TCNWF on climate predictions and projections, and actually and also in evaluation and quality control. He will tell us more about tools and also enhanced C3S climate predictions and projections. Thank you.
Yeah, thank you, Chiara, for the introduction, and also Anka for nicely setting up the presentation, as well as Ellie before, actually, on EQC. So firstly, I just want to start by thanking my various colleagues who I work with at ECMWF, who are listed on the slide here, as well as the wider group of people who work on C3S and make all of this possible, but also especially the contractors, who I haven't included throughout this slide deck, but of course especially on climate projections, most of this work is made possible by the contributions of the contractors rather than work we do internally. So I just want to start by thanking everyone who works on this. So I'm showing again the same slide. So I'm starting with this, the same slide Anka showed earlier, showing specifically for predictions and projections some of the different aspects of the service and those that are made available to users. So these are applications and graphical products, data products, as well as tools. And with the yellow arrows, I've highlighted a few of those which I'm going to talk about more in a moment to really put into practice what this means for a specific user answering a specific question. And hopefully that helps bring to life how in this field of predictions and projections, the service in some ways is more about enabling users to create their own authoritative information that's relevant to this specific use case, rather than us making all of those decisions for them in advance. So it's really about enabling the downstream use. Another thing I want to mention is that at the bottom of each column, I acknowledge here that these data sets, products, and tools all sit within the wider offering of things available from C3S. So for example, on we have sectoral applications related to these applications and graphical products. For data products, if you go to the CDS and type in climate projections, you'll also find derived data sets which come downstream from things like CMIP6 or from the seasonal forecasts. And the same also applies to the tools. So we have C3S data tutorials, which I think we'll hear more about tomorrow, as well as a Jupyter Hub where you can run some of these on our own infrastructure. So to put some of this into practice, I'm going to go through, to show how this could be put into practice, go through an example user workflow. So starting on the bottom left here, let's imagine we have a task for a specific user where they want to create charts of projected changes in the future for a specific set of climate indices for a report that they're preparing, and they also want some information on model performance, whatever that means for this specific use case, whether that's about the quality of the underpinning models, biases, how well represented variability is, for example, El Nino teleconnections that Anka's just mentioned. So yeah, we're going to be looking at future projections. Let's say we're looking at cooling degree days as the index. And then given where we are, let's choose Hungary and the wider Central Europe area as the area of interest. So the first step here in a user workflow could be to go to the C3S Atlas that Anka has just mentioned and locate the specific index that they're interested in. You probably can't see it very well, but on the top right is a screenshot from the Atlas interface. It's a small sort of part of the wider range of indices and things which are already available as pre-computed products. So once you've done that, you can select a specific region of interest, either user-defined and essentially input it yourself, or in this case, we select a European country, Hungary, as the region of interest. And then the Atlas will already produce essentially a wealth of regional charts, of which I have two examples here, automatically. So in the middle, we have the time series of the projected future changes to this index. For the Eurocodex ensemble. So we heard some information about the use of Eurocodex in Hungary earlier today in one of the first talks. So yeah, that information is shown here. And then in the bottom, we have a climate stripes-like plot, but in this case, each horizontal row of pixels here is representing a different member of this Eurocodex ensemble. So essentially, it gives you some information about do the models agree and what is the uncertainty. So some users could stop here because you already have the charts from the C3S Atlas. You can output the charts in various formats or the data behind them. But in this case, we know the user wants to change some things about it, to customize the charts themselves. So then they need to go to the CDS and download some data. So the C3S Atlas dataset, which underpins the application, is available on the CDS. So in the top here, I'm just showing how in that data set, you have access to all the different data, underpinning data sets which are available, but in this case, in a harmonized, in some cases, bias-corrected fashion, which greatly improves the user experience. So for example, here they can select Eurocodex as their climate projections data set. They could extract a sub-region, which means they don't need to download data for the whole globe. They can just extract the specific region they're interested in. And then they can also choose a reference data set. In this case, they've chosen EOBS. And then when downloading that, you access a data array, which is something like the thing on the bottom I'm showing. And that might not mean much to all of you, but for those who've dealt with climate projections data, you can probably recognize that it'd be very nice to get something like this back from the CDS instead of needing to go to the underpinning Codex catalog entry and need to download every combination of GCM and RCM that exists, as well as the ensemble members, and then try to merge them all together yourself. So this is already a nice step along the way to creating some customized products. And then finally, the last part of the story is these user tools and also the EQC that's already been mentioned. So as part of the C3S Atlas user tools, which is a repository of Jupyter notebooks wrapped together with documentation and examples, there are some there which allow you to reproduce some of the charts. So here I've just highlighted some of the headings. So we have one on time series, we have one on climate stripes, and then also we have ones which show you how to reproduce the underpinning index and to see how it's calculated. So we have one about the cooling degree days also available. And with those and the data that's been downloaded, a user could then essentially recreate those plots tailored for their specific purpose. And to answer the second part of the question, which was about the quality or the model performance in this case, they can go to the underpinning data sets, click on the EQC tab that I think Ellie mentioned, and then they would have information available in the form of Jupyter notebooks. So specifically in this case, we could go to the the Codex catalog entry, click on the quality tab, and then find some relevant quality assessments. So one example I've put on the screen here is about bias in extreme temperature indices. In this case, it was within the context of the reinsurance sector and for this specific use case mentioned, but their conclusions are relevant more broadly. Here they also looked at a specific subsample, but again, since this user now has access to the data from the C3S Atlas dataset, they can apply the same kind of methods from this Jupyter notebook to the data they're now going to use in their charts. So hopefully with this is going through this in some detail has shown how these three different components fit together. And what I also want to mention is that this kind of workflow is also possible for seasonal forecasts. As Anka mentioned, we now have some Jupyter notebooks about how to reproduce the graphical products, including the Niño plumes, well, parts of the Niño indices plots that were shown. So this would allow a user to go through a similar process also for seasonal forecasts and create customized plots for their region, for their specific use case. And as Anka mentioned, something similar will be coming for decadal as well in the future. So now I just want to finish by going through 3 new capabilities related to what I've just been talking about. So the first is a bit of a under-the-hood thing that most of you will never interact with, but Anka's already mentioned it and it is important. It's about the QC of the climate projections data. So here we don't have, of course, contracts with every producing center who produces climate projections information and uploads it to ESGF, which is the underpinning research infrastructure. Instead, we have contracts which acquire data from that infrastructure, curate it, quality control it, archive it, and then provide access to it for C3S users. And to do that, the quality control aspect is very important. So what's changing here is that we'll have a new modular and configurable quality control framework that will be used. So this is something that's being done partially funded by a C3S contract, but also in the context of the wider community. And this means this will be something that can be applied during C3S dataset preparation, but also adopted more widely by the science community. And as Anka mentioned, this has recently been endorsed as the QC approach for CMIP7 data on ESGF. So this will be useful in a couple of ways. So one is that C3S users will have access to the outputs, essentially, of this quality control procedure, and to be able to understand, for example, why some data they see in a paper that's come from ESGF is not available on the CDS. But it will also be useful because if it's being used, for example, for CMIP7, that means more of that data on the research infrastructure will meet our own quality control standards, meaning it's available for use by CDS users and also for the derived data sets and applications I mentioned earlier. So a last element of this is that since this framework now will be modular, configurable, and more easily repeatable, it will help us with this sort of workflow or timeline I have in the bottom right, which I don't expect you to be able to see in detail, but it essentially shows that over the next few years there's going to be a lot of activity in the space for C3S with, as Anka mentioned, new regional climate projection data, DCPP, so decadal prediction updates every year, CMIP7 data coming in the near future as well. So with all of this, having this repeatable operational quality control framework will be very useful. And then the last part is that this could also be used more widely, so for other scientific projects or for other climate service contexts. And just to mention here that the lead for this, both from the C3S perspective in a contract, but also the wider research community's perspective, is around this week. It's Guillaume from IPSL, so if you have any questions about this, I can put you in contact with him and we can discuss it at a coffee break. Moving on to the next thing, so Anka's already mentioned this. We have this new decadal prediction service which has started. Here I have a table. I won't go through it in detail, but it essentially shows we'll have a far greater offering of variables output at different temporal resolutions and on different pressure levels than we had before, and also on single levels and some ocean data. So this is vastly improved and increased compared to what was there before. And then we'll have, as Anka mentioned, example applications, but possibly more importantly, tools. So the workflows behind those applications will be available to be customized, for example, changing the region that they're applied over, but also more fundamental things like bias and drift adjustment tools will be available, as well as an evaluation framework, all enabling downstream use of the data. And then the last update I want to mention is that the C3S Atlas, which I've just been talking about, but also Anka mentioned, was updated last week. So we have extensions to the reanalysis and one of the observational data sets to bring them closer to real time. But the main update has been to the application. So I don't want to give too much away about this because there will be a demo booth session tomorrow, but to highlight a couple of them, you can see in the top right here the new improved design, which facilitates navigation and product selection. And then in the bottom right, you can see a new feature, which is this side-by-side comparison of data sets. So I think this is very powerful because, for example, here we have the lower resolution ERA 5 reanalysis on the left-hand side and the higher resolution Copernicus European reanalysis on the right-hand side. And now within the Atlas application, you can have them both side-by-side and drag this bar, which you can see in the middle, to one side or the other to see what the differences are. And this also applies, for example, for comparing the higher resolution climate projections outputs to the lower resolution ones. And last but not least, there will be new user tools available, which I mentioned at the bottom there. So again, increasing the pool of examples via Jupyter notebooks, which users can draw from to create their own products. So I have a summary here, but I won't run through that again. And I just also want to mention that all of the links to the various things I've just mentioned are available in this last slide, so you can refer back to them in your own time. Yeah, so that's all I had. Thank you for listening.
Thank you, Chris. I think we will come many to the booth now of the Atlas. So questions for Chris. We have, I think, time for one quick question. And I think your example workflow could be also an AI agent, no? Yeah, okay. Questions for Chris? One question for Chris. But I think Chris will be here. For the entire. Yeah, we have Anka.
Just to add a small point, neither Chris nor I remembered to say that the work on decadal predictions involves the WMO Lead Center on Decadal Prediction, annual to decadal prediction. And we try to complement what they do and to enhance the information that's available to users in addition to theirs.
Yeah, thank you. Very relevant specification. Okay, so let's thank Chris again. And I think we have now our last speaker, Barbara Wassen. I cannot see her. Here she is. She's an associate professor at Esterhazy Caroe Catholic University. She's also the former Deputy Minister of State for Climate Policy and Ambassador at Large for Climate and at Ministry of Energy. She's an accredited ESG advisor and an active member and mentor in Women in Energy and HBLF. So welcome, Barbara, on stage. You will tell us about the need for actionable climate information in a constantly changing geopolitical arena. Thank you, Barbara.
Welcome all of you to Hungary. In my role as an ambassador, welcome all of you to Budapest. And welcome all of you to the Pest side of Budapest. And I'm not sure if you know in what building we are. But this building was designed by a Dutch architect called C3S, who gave the name CET, Central European Time. CET is pronounced in Hungarian Cet, and Cet means whale, the sea mammal, because it looks like a whale. It represents power, it represents dignity, it represents the dynamic flow of the Danube and all the living ecosystem in this beautiful river. But there is something people forget. We are in the stomach of this whale, like Jonas from the Bible was for 3 days. And you will be in the stomach of this whale for 3 days. The question is, what you will do afterwards? Will you go back to your own Nineveh, to the evil Assyrian capital? Will you spread the message? And what message you need to spread on Friday when you go back is what I'm going to emphasize in my presentation, which is leading you a little bit over to the more informal part of this evening. And the sentence is, facts are stubborn things. So let me talk about why we need scientific facts for actionable climate information for climate decisions in a constantly changing geopolitical arena. I work as a university associate professor, but at the same time I'm doing climate policy. And what I frequently see, that scientists don't understand climate policy, and climate policy makers don't understand climate science. So let's bridge the two. Let's not work in silos anymore. And let me start with a recent study, which is saying that basically you are unambiguous because what you are saying is pretty much consequential. But what economic models say is not reflecting actually what you say. There are cascading risks, there are cascading failures in a constantly warming planet, and climate policy is not answering to these cascading events. We can't bail out the earth like we did the banks during the economic recession. And this is actually in the very bottom, the source of the Guardian article, behind which you will find a 200-page study on the reality of climate science. Because we are living in a paradigm shift in which the speed, the scale, and severity of risks driven by climate nature crisis is aggravating, and governments are dangerously out of touch when it comes to reality. Some of the quotations from this study. These economic models think that with a warming of 3 degrees, we might lose 10% of the GDP. No. With global warming of 3 degrees, society and economy, as we know it today, will cease to exist. And we need to reflect on what science says. This is also a recent study. In the World Economic Forum, there was a study, they were asking 5,000 world leaders, what do you think the biggest global risks are in the next 2 years and the next 10 years? Look at the colors. In the next 2 years, we are going to have a lot of geopolitical problems, as we have currently today, and some connected to misinformation. But look at what they think about the next 10 years. The green colors pop up. And not environmental pollution, but extreme weather events, biodiversity, and ecosystem collapse, and critical change to Earth systems. And of course, a lot related to AI. What I think as a climate diplomat is there is a new multipolar world emerging from a unipolar world. Certain country groups like BRICS are getting stronger and stronger. New countries joining BRICS countries. BRICS countries are not going to increase in size or population or GDP or import and export. But in one thing, yes, with the newly joining countries, 22% increase in oil production. And that has changed climate diplomacy. That has changed what's happening in UNFCCC, in IPCC, everywhere else. Because BRICS countries have become more and more vocal in what they represent, the increased ratio of oil production. And in 2 years' time, we are heading towards COP33, which may not be in India, it might probably be in South Korea, whereas you can see the G20 event will be. Don't underestimate the role of politics when it comes to science. I know that, yes, that year is also the US presidential elections, and I keep saying that we should not mistake, we shouldn't judge a cycle for a trend, and I keep believing it. But because if we do, if we judge a cycle for a trend, that might result in misallocated resources and poor long-term planning. But why is that red circle so important? Because that's GST2. That's the second global stocktake. That's when we have to decide on the next 10 years to come. And what if IPCC 7th assessment report doesn't arrive at GST2 in 2028? Then science will not lead climate policy. Who are blocking it? BRICS countries. And why are we here for 3 days? To help this work, that the IPCC AR7 would be there when it needs to be there. Why? Because I do believe in the Paris Agreement. Why do I believe in it? Because it provides a significantly and scientifically based risk-decreasing framework for a problem that cannot be solved by one single party to the convention, by one single country. This is not a mathematical problem, but yes, from the triangle of inaction, we have to make a circle of cooperation. When we are not finger pointing to each other, when there is synergy. If it's a zero-sum game like this, then the most vulnerable will lose. But if we can cooperate, and this is what the IPCC says, that we need to cooperate because synergies, systematic changes can bring about real changes. I told you we shouldn't mistake a cycle for a trend, and the political debate may suggest a slowdown in climate ambition, but real economy tells a different story. The famous pincer. Yes, GDP has grown by 31% between 15 and 24, while emissions increased by more than 9%, which means the pincer is opening. That's good news. And especially in PV and battery and rapid deployment of clean energy. There's something else you may not know about Hungary, and I'm a very proud Hungarian, is that in terms of PV ratio of power generation, Hungary is a world leader. In 24, it was 25%. In 25, it's more than 28%. 28% of power generated in Hungary is coming from PV. We overtook Chile, we overtook Spain and Portugal, everybody. We are world leaders in that. So clean transition is happening. But in what fields? Let's have a look. If you go back to 2005, clean energy investments were happening. But from 2013, electrification of transport was coming in. Well, buildings have not been given enough attention, in my opinion, but also industry is greening. And by whom? That's the next slide. Of course, China is a world leader. Next one is US and Germany. But look at number 5. India is there. And look at some other BRICS countries, or those who are aspiring to join, like Saudi Arabia, number 10, leading in clean energy transition. We used to live in a world of free trade. Now we have tariffs. You might say tariffs are the unintended incentives for clean energy transition, whatever they are, but it's happening, and this is good news. And finally, climate action is also an opportunity to avoid future costs, because the costs of inaction are growing up. This OECD report that I'm going to show you has just been released 2 weeks ago. And just, it's going to be available. I'm not going to read it. But the extra very hot days that we can expect because of El Nino, for example, they will reduce labor productivity by 0.3%, which might mean 80 million full-time jobs by 2030, especially in outdoor sectors. This is cost. And there's a rising cost of inaction because of floods, sea level rise, and water stress. And look at this one. These are the economic losses from climate-related natural disasters in OECD countries. They are rising. There are some years where they are even higher than ever before. But there is a constant rising trend. Facts are stubborn things, and we cannot step out of scientific reality. Right now, you are in the stomach of scientific reality, but make sure that you bring this news back to Nineveh. And the Hungarian aspects, although it's going to be shared later by the CEO of the Hungarian Meteorological Service, Hungaromet. Just a few data. Look at the map in the top right corner, which is actually about this April, less than 6 weeks ago, and the percentage of precipitation compared to 91 to 2020. It's really alarming. And I think from the presentation of Peter Koiner, you already saw the other one. There are 2 RCP scenarios, 2.6, 4.5, and 8.5. But the lookout for Hungary is not really positive. And the cold facts have already been shared. They are not too cold for Hungary. And Hungaromet, the former Hungarian Meteorological Service, which is now a state-owned company, and its duties in this corporate structure have become more commercial, but also it was taking over its public duties. But it has really expanded in many areas. Under the framework of the Open Data Directive, we really want to reach decision makers. There is an umbrella website from which you can reach climate data. Also, the NOGIS, which is a National Adaptation Geoinformation System, which actually has hundreds of layers across 18 climatological and vulnerability topics. And it demonstrates climate change tendencies and consequences. And last but not least, I think a lot has been said that these geopolitical challenges, the unintended incentives, can really lead to regional aspects to gain momentum. That's why we work a lot in this CET region, Central European region, especially something else you might not know. We have the Visegrad 4. There are 4 countries sticking to each other, Poland, Czechia, Slovakia, and Hungary, because we really concentrate on the regional aspects of all economic and also environmental and climate decisions. So just to wrap up, before I say thank you to you and give over the word to the CEO of Hungaromet, is that this is like heat and the fury. Climate change is like a thermite, you know, these small ants which are eroding those institutional and community frameworks on which we normally rely on in times of crisis. Remember, facts are stubborn things. Nobody can step out of scientific reality. Those who deny scientific reality will not protect sovereignty. They will not protect the well-being of their country, and they will not provide security for their country. Denying climate science will undermine all three. Thank you for your attention.
So, thank you, Barbara, for your reflections. And I think we are at the end of the session now. And before going to the icebreaker, I would like to join you and thank Gabor Gyulasanka. Please come on stage. Thank you. The CEO of the Hungaromet, and he's our esteemed host. Thank you very much for hosting us. Thank you for having us here, and thank you for connecting to, the community. So I think I'm happy to invite you to give a few words of welcoming, and yes, for the icebreaker. Thanks.
Thank you very much. As I understood, we had a long day today and lots of useful information. And to be honest, I was not going to talk about the Hungarian climate change prospects because I cannot summarize them so well in such a short time as we have just seen it a few minutes ago. I was going to talk about this building, which luckily just doesn't work out perfectly because we have already had one introduction on this. However, there's a small side information you forgot to tell. We are in the Közraktár Street, which actually got its name after those buildings that used to be here. When the CET was designed, it's actually using those old warehouses as those older components, those colorful components within the modern frames, which means we are connecting our past and reusing our past for the future. And I think with the climate information, we are doing something similar. Right now, we are using our past. We are watching what's happening currently, and we are connecting in the future and trying to tell the decision makers what we have to be prepared for and how we have to act so that we can really proceed into a safe future. As for our evening, when I came a little later in a break and I heard lots of noise there, lots of discussion, which is, I think, one of the key points of such meetings. Talking to each other, exchange information, exchange practices, exchange experiences. And I would like to welcome you to our tonight's icebreaker event to continue what started already in the breaks and to start the discussions before the upcoming presentations tomorrow and on Friday. Thank you for being here. Thank you for being so well prepared. And I wish you a really fruitful conversation for the following days. Thank you.
Okay, we are free to go.